हो जाएगा ना, तो यहाँ से Okay. Is it there? I think it was.
Sure. As,
Whatever is convenient.
yeah, वो better है yeah. चल वहीं बैठ.
Then I have to do this. Ladies and gentlemen,
You want to come here?
yeah. Dr. Goel, Dr. Bipin Kumar, Dr. Nand Kumar, and all distinguished friends over here. Sorry we got delayed because our delegates couldn't come. So we are postponing everything by half an hour. So you can add 30 minutes to whatever is written over there. And we have a question of half an hour in the program. So I think we should be able to make it. I'll only briefly introduce because we have our experts over here who are actually working on hydrogen. I don't have any pretense of working on hydrogen, but whatever I've done, okay, it's basically my personal reading. But I think I'll just introduce the topic and I won't take much time, but I'll leave it to the experts to really speak on that. One thing, though I spent all my life in oil and gas, but I'm absolutely convinced today that the source of future energy is hydrogen. The days of oil and gas and fossil fuel is over. Not because of economics, not because of energy audit also, not because of anything, but because of climate. And there's no other reason for it. So that's what is it. We are going through a major transition. And what has happened is with this transition, even the geopolitics is going to change. Geopolitics which was there when fossil fuel were dominating is over now. And we are going to a new world, a new geopolitics where countries like China, Congo, they'll become very, very important. We know the reasons for it, as I already said, and people have been discussing it, so I'll not waste time on that. And I'll come to the reason why we think hydrogen would be the future and not solar and wind. One of the reasons for solar and wind, apart from other things, is that it's not in our control. Even today, I was reading in the morning paper that China is thinking of sending satellites up so that they can get a continuous supply of solar. So that kind of work is happening all over. But still, I believe it will be the hydrogen which will take over. You talked about the lithium-ion batteries. The main the main issue why lithium-ion batteries are not going to work for everything else is basically because they need much more charging. They are good for light vehicles, but they're not really good for heavy vehicles. So that's the main reason why they are not the real replica. They can work for local distances and moving the car and all that within the city. They're fine. So that's the main reason. The charging takes much more time, okay, compared to the hydrogen fuel cell. So this is basically now the thing is how do you produce hydrogen? We could produce hydrogen from fossil fuel using nuclear energy and using renewable energy. The one we talk about renewable energy is the one which can produce your green energy, green hydrogen. There have been different labels which have already been discussed, so I'll not waste time on that. So basically, what we're looking for more is electrolysis and maybe gasification, where we are using only renewables. That's what will give you the green energy. The rest will give you blue and gray and all kinds of energy. Okay, so that's what is given. How is green hydrogen is generated has been discussed, so I'll not spend through steam reforming. The blue hydrogen, the only difference between blue and gray is that blue hydrogen, you also have the carbon sequestration process. Green hydrogen is what we are talking about, where I think called the fossil fuel involvement. But as on today, the percentage of green hydrogen is far, far less. This has to go up if we are really want to save this earth. If you talk about this is a projection given by I think mRNA, they have come out with it, and they say by 2050, it is the green hydrogen which is going to dominate. Today, it's not, but it's going, that's what the whole switch is all about. This is a new method which I would spend a bit of time because this has not been discussed in these last 3 days. This I was reading in a Berkeley paper. This is a research work that is happening in Berkeley. They're trying to use solar, straight sunlight to split water. And it's called photocatalytic water splitting using a catalyst into hydrogen and oxygen, using a semiconductor catalyst. This involves four main steps: generation of electron hole pair. So students would understand what is the electron hole pair. From light irradiation of the anode, the oxidation of water to produce oxygen molecules and hydrogen ion. This hydrogen, then electrons are coming from the external circuit, and that will make hydrogen ions back to hydrogen molecule. So this is a method that Berkeley is trying to advocate, and it has been utilized, but not much. Maybe that this method can come up, that may be cheaper than electrolysis. But the whole point that I'm trying to say is there's a lot of energy, a lot of work that's being done on finding out a cheaper hydrogen, because as on today, green hydrogen is much costlier than gray hydrogen or blue hydrogen and all that. Okay, so that is one of the reasons why. And the second thing which you also understand is there is a concept called energy return on energy invested. When we generate hydrogen, we're actually spending much more energy than what the energy hydrogen will give. So that is another basic problem which we have as on today. So these are the areas where a lot of research work is happening, and my friends will talk about what is actually happening. So now why hydrogen is going to the future. That's the end use. If you see the end use, everywhere you can use hydrogen, which you could not have done with the lithium-ion battery. Starting from industry, starting from transport, starting from house heating, starting from power generation. Everywhere we can use hydrogen. This is the main why hydrogen is going to be the future. This is the slide which I wanted to stress on, right? The priorities, if you go, the chemical refineries will be there, steel, long-haul aircraft and all that. The kind of pollution that aircraft generates is unbelievable. And the interesting story was, this time in Davos, when they all met for clean energy, the number of private jets that went over there much more exceeded, became a joke that these people, they went there and they talked about clean energy, but the number of jets that went was fantastic. It was too high. Okay. The main issue of hydrogen today is hydrogen storage. Okay. I'll just talk briefly about it and I'll leave it to Professor Vipin to really get into it. Hydrogen, what are the issues of hydrogen? Hydrogen has occupies much larger volume. That's where the issue is. So if you want to drive a car with hydrogen, the amount of space the fuel will take is 3 to 4 times what our normal fuel takes. And this is what is a big impediment. This has to be sorted out. And how do you do it? So how do you store hydrogen so that this doesn't happen? Because if you store hydrogen through normal processes and high pressure and all that, gas, that is where the problem comes. So basically, it's over here when you talk about the gravimetric densities. Over here, the volumetric density is very low. It increases, the performance improves with high temperature, high pressure, but and low temperature. But yet, it's not anywhere near what we are used to today. So that's one of the impediments. So that is why what has happened in the recent years is what is called solid state storage. So basically, it's chemisoption and physioptions. So these are the two methods through which hydrogen storage is working today. Hydrogen can be stored, densely stored in materials at low pressure. There are two types of metal hydrides. There could be intermetallic hydrides and there could be complex hydrides. And these are all atomic hydrogen. These are not molecular hydrogen. The basic difference between physioption and chemisoption is in chemisoption, you are using atomic hydrogen. Okay. And physio, you're using hydrogen as a molecule. That's the basic difference between that. And this is basically a chemical reaction that's taking place. Okay. And hydrogen is released from chemical hydrogen storage material through non-equilibrium process like heating and all that kind of stuff. Okay. The basic difference is in between metallic and complex hydride is in the metallic, hydrogen is present as an ionic. It's an ionic bond, while in the complex hydride, it is the covalent bonds. So that is the fundamental difference between ionic and covalent. Okay, and the description of there, like say, the A element is normally a rare earth. Now that is where the geopolitics is changing. Rare earth metals are much more abundant in places like China, and therefore the politics are going to change. In fact, that is precisely why China is ahead in the race. And China is going to come up with green hydrogen at less than $1 a kg very soon, much faster than other countries because of that. Okay, so India is, I think, 7th or 8th place. I think I'll show you that list if I have it. The formation of metallic hydride is an exothermic process. So if you can take that heat, and when you want to heat hydride back, if you can use that heat and recycle it, the cost comes down. So those kind of innovative ideas are required for doing this. Okay. the rest is all. Then nowadays, what is happening is even people are talking about magnesium hydrides. So that may be a better way of using it. Okay. So a lot of work is going on as far as hydrides are concerned, either it's metallic or complex. So this is one area of storage where a lot of emphasis is being given. And I think Mr. Bashni is going to talk about the practical usages of it today and which companies are doing it and which companies are not doing it. So that will cover up the storage part of it. In fact, today, maximum research is not on production generation, but maximum research is on storage. How do you store it? That's because of the volumes and all that involved with it. A physio option, as I was telling you, it is basically molecular hydrogen that can absorb into the surface of porous solids, providing this is again hydrogen sorbents are high surface areas, microporous solids, activated carbon, metal organic frameworks, MOFs are another area of research where there's a lot of space, and that is where hydrogen is stored. So MOFs are also becoming a major area of a new research area of this thing. Okay, and the able to undergo sufficient charge and discharge cycles to last life. These are some of the basic conditions in which they are accepted. Okay. So MOFs, I told you that they are porous crystals made of metal ions, and in the pores you store hydrogen gas. They have surface areas and hydrogen absorption capacities are high. MOFs can also store liquid hydrogen. That is another thing about it. And again, a lot of work on this is being done in Berkeley, right? So hydrogen, this is what sums up in short how hydrogen can be stored in physical based and compressed gas, and these are the very standard methods, and cold and compressed this thing and liquid hydrogen. But material based using adsorbent and absorbent within hydrides, complex hydrides, and chemical hydrogen are now taking places. Okay, plus MFs. These are the main areas. Summarizing, storage of hydrogen as a pressurized cylinder is not likely to be applied in future. Liquid hydrogen could be applied. Metallic hydrides of heavy metals cannot get rid of the constraint of gravimetric density, but they are still there. Complex hydrides are still in the domain of research. And the absorption of hydrogen. So these are the basic methods through which are the main areas of challenge, and which where if we can cut down on cost, hydrogen storage problem can be sorted out. Areas of concern: high production cost of fuel from green hydrogen. This is one area. Lack of infrastructure. That is where the policies and all that will come up, as we are saying. So unless and until we create, and it's linked to the demand, unless and until we create a demand, the infrastructure will also not come up. So it's a case of chicken and egg problem. So this is one area where this thing. The next area is what I was trying to tell you: energy return on energy invested. The energy losses are very, very high. So, and there is no way, because when you're transforming one energy to the other form of energy, you are going to have a loss. That's the basic Carnot cycle. So you can't avoid it. That's the basic principle of thermodynamics. So that is an area of concern. And lack of value recognition. We need to have values. We need to have values for green hydrogen, green steel, green shipping fuel. There has to be additional values for it. And the point you was discussing with them is, it's not economics which is deciding it today. People have to understand that fossil fuel definitely is cheaper, even $100 a barrel. But we cannot afford to use fossil fuel because we want to save this earth. And if we include the environmental cost, then naturally this will be cheaper. So it will just be a holistic thing. And you need to, that is what ensured sustainability. The main thing is sustainability has to be there. We can't, destroy the earth. I think this is the kind of funding which is being done. European Union, especially with the Ukraine war, is spending a lot of money into it and going much more into it because they no longer want to depend on Russia for gas, right? The hydrogen consumptions in military tons per annum has been shown. China is already taken the lead in that. Okay. Then producers of critical material. Again, these are the main critical materials which are used for production of hydrogen in those and storage in terms of hydrides and all that. And again, China is again in the lead for so many rare earth metals. So that is what they are endowed with, and nobody can help it. And the countries in which green hydrogen could possibly become cheaper, China is probably going to be cheap. This is hydrogen, green hydrogen be cheaper than blue hydrogen. That means you produce hydrogen from fossil fuel, do the sequestration, that is blue hydrogen. Yet green hydrogen, you are doing it through electrolysis or things like that. But we want green hydrogen to be cheaper than blue, and China probably can reach it by 2023 itself. So that is phenomenal. This is what I got recently from one of the Bloomberg's prediction. Okay, I think thank you very much. Now I'll invite Mr. Dr. Bipin to really come up, because he's been working on hydrogen. I'm not working on hydrogen, I can see. So he will now come up with this thing. I think I've done the introduction of the topic. Okay. Thank you.
No, it's not a display mode.
You please introduce a little bit.
Okay, okay, okay.
Yeah.
Yeah. Give your.
So,
Should I introduce you?
yeah, it is.
Dr. Bipin Kumar Gupta, he's a principal scientist in CISR, NPL. He has been working, as he's telling us right now, he has been working with hydrogen for years, for decades right now. And he is actually involved with the work. I mean, you would have patents and all that by now.
Yeah.
So he has,
Metal hydride.
he has patents in metal hydride. I just talked about it. He has been working on it and he's got patents on it. So let us listen to the expert right now. Okay, thank you.
So good morning to all. It's a pleasure to be here, and more pleasure to I can talk about the hydrogen, because my journey starts from the lightest material. But you know, India-like scenario, sometimes when you came in job, then the scenario is sometimes going to change. And when I came to NPL, then my responsibility was to lighting material. So my journey is from the lightest to lighting. So I will just to talk about today the lightest material, how we can use for the fuel, and how it is a green fuel. So it's absolutely correct what the previous speaker mentioned about the climate, because we are using our environment or climate like a umbrella. If it's a good temperature, then we are saying aaj ka weather bahut acha hai. And when it's like very hot, then we can say like that, just to start the AC. But we never think about how we can contribute to climate, what climate given to us a lot of things, and how we can save that. So if you talk about this kind of the area, not only the climate say, but also the second part is like my title is like hydrogen energy as a freedom fuel. Why I'm talking the freedom fuel? Because last many years we are importing the hydrogen, and more than 70% money is going to just to invest to import the hydrogen. Means petrol. So to how they replace the petroleum, that kind of the investment, how we can enhance the GDP of the India by making the indigenous this kind of the fuel, and can use for the two-wheelers, three-wheelers, four-wheelers, and many places. And I will show like how hydrogen can be a replacement of the petrol or CNG, and how it can be better than that. So I can just in this display just to show how you can feel and touch for the hydrogen vehicles. And also the left side you see I get the chance in Japan, and I also seen the vehicle run on the hydrogen. And I also get the chance in Japan to ride on the bus on the hydrogen. So I can compare with the what hydrogen technology we developed, that is the right one, and drive by myself the time when I was done the PhD. And left side you can see for the Japan vehicles. So I will talk about the details, and I will also talk about details about the storage. So before I can start my talk, I want to dedicate my guide to this work, because he is the person he started the India the first like the hydrogen, because that time only 2 persons working on the hydrogen, like MBC Sastry from the IIT Madras and Professor O.N. Srivastav from the BHU. So I get a chance to him, and I learned a lot from him. I can say as a dedication to, he's a person, a man composed like a book of learning infinite chapters, because if you talk to him, the different areas he's working. So that kind of the, inspiration from him. I also work like nanotechnology or like the lighting materials as well as the hydrogen. So he's a person I can say he's an Iron Man of science and full dedication, consistency, hard work with passion. So these things are very important for the students. If you really want to achieve something, then goal and you between the notes should be there. If you want to, some goal to target, then you and goal will be only the main person. No third can enter in that. So then on you can achieve the target. And just to recently, Professor Srivastava no more with us. So this is my mission to take a mission to how I can contribute again in this area and how can India. So what are the experience in this area? I will contribute time to time to commit even now from the this talk. And anywhere if required this kind of the experience, I will just to contribute whenever required. So I also wrote a review for the memorial of Professor N. Srivastava. So already I wrote in this review regarding the how India started this kind of the work and what are the achievement till date in India for the hydrogen, not only the storage, not only production, but up to application.
Share the copies of this article
sure,
with the participants.
And before live to show the things, it is incomplete. So you can see how the hydrogen vehicle is going to run. This is our physics department. And we taken a project from the MNRE for the 40 hydrogen motorcycle. So we made the metal hydride in kgs and converted to hydrogen fueled motorcycle there. Still, if anybody feel to see this kind of the technology, they can visit to BHU because other group members are working. So if you see here, this is the motorcycle run on hydrogen. And so auto also 3-wheelers on hydrogen. So myself also riding left side. In BHU campus. So, and this is the article also we published in IGHC, International of Hydrogen Energy. That is the hydrogen, what kind of the advantage and this vehicle, how we are making in BHU and what are the indigenous technology we are used for the storage. So everything in that article also as in use and views in 2004, that article. So we also taken the project from the Sonalika tractors from the Punjab, and we also converted to hydrogen 3-wheelers. So now even also 4-wheelers we are converted in hydrogen. So the idea is I will touch these points, how you can store the hydrogen. And if you compare with the hydrogen with the storage in metal hydride or storage in the carbon nanostructures or storage in the sodium alanates, like this previous speaker talked about that, what is the advantage and disadvantage? When you talk about the physioabsorption or chemoabsorption, it depends upon what kind of the application you're trying to touch. If you're talking about the physioabsorption, the kinetics is very slow. Because compare the enthalpy of the physioabsorption and chemoabsorption, it's almost like 2 times higher in case of the if you talk about the metal hydride. So if the enthalpy difference is there, then the kinetics depends upon the enthalpy. So in case of the physioabsorption, you will not get the plateau. So once you will not get the plateau, you cannot use the hydrogen for any kind of the stable application. So if you use in the metal hydride, why it is safe and why it is useful? Because there is a plateau for the hydride phase. So that plateau can be utilized the constant hydrogen for the vehicular applications or any other applications. And what is the other reason why we are using that? I will talk in the next few slides. So first, already previously we touched about the why we are using hydrogen, because we can produce hydrogen from the water. And again, we use the hydrogen with the oxygen and combustion, again make the water. So recycling of water is there. And you can see if we can use this kind of the fuel, what is the other advantages? If you see here, the main advantage, like I said, the fusion fuel, if you come see this data, so if you see this data, and you can know about this the Indian scenario. So if you see the primary energy used globally, it's like it's a data is in 2006 data. So if you nowadays it's order of magnitude, it may be higher. So what the emphasis I want to give there, why you are thinking about the hydrogen, you can see this slide, why the transition is required, because we start from the fuel wood, right? And then slowly and slowly we are trying to reduce the, if you reduce the ultimate carbon whole, then ultimately hydrocarbon is converted to hydrogen. So that's why we are going to that transition, and obviously it will happen. No one can stop it. We can talk now, but we have to sometimes to just to force to use. So ultimately, this transition, if you see from the wood to petroleum, and then you see the CNG. So ultimately, now we are talking about the hydrogen. So if you see the present scenario, India consuming like 5th in the world for the energy consumption, even more than it may be, because this data is the MNRE from the 26. So if you take the data from the 2022, it may be India is 3rd, or it may be the 4th place. Because, pardon? 4th place, yeah. So so this scenario I want to put, because we have to think seriously. If you're not serious about next 10 years, then we have to again face the major problem. And it's not a joke kind of the things, because we don't. If you see the condition of the India for the oil reserves, in list India is not there. So ultimately, if we have no our own policy or no our fuel, then ultimately we have to depend upon the others. So nowadays we are 70 to invest. It may be 90%. If you are investing more and more to import the oil, ultimately you have to compromise some other places. So that compromise will be like the expensive your foods, expensive transport, and everywhere. So it's very important to we can think about this area. So measure the reserve in the Middle East or these places. I already shown in this DOE data. And other reason why we are using the hydrogen, because already we are using the mask because of the corona, but we also projected many years ago, it may be that mask will be there in people living in Delhi because of the pollution. So much vehicles are here. We have the no policy for the vehicles. Like if you go to Japan, first people ask you have the parking, then they will sold the vehicle. But in India, anyone can use 3, 4, 5, 6 vehicles, and even there is no space for the parking. You should forget the pollution. So these kind of the policy is very important. So if you see the foreign exchange, how much going to invest for the India side, so it's almost like 70% that time. It may be more than that now. And recently, Prime Minister also agreed with this data, and he told in 2 days ago about this kind of the import. We are depending on the other countries, so we have to talk about the hydrogen. So what are the benefits now? We can talk about that. So there is several benefits. If you talk about the combustion of the hydrogen, compared with the CNG or compared with the other hydrocarbon gases, so it's a like green fuel. So outcome is like water. So little bit the NOx. So it's a, you can say also it's a very important for the climate. So if you want to green fuel, then what is the program for the hydrogen? So major part is the production, delivery, storage, and fuel cell and technology validations. So technology validations are very important, because I've seen many places in India working for the hydrogen, but nobody has any quality lab, nobody has any rules for the hydrogen, nobody any manual, and last many years they're working. And even the funding is going for this kind of the different institutes, but nobody bother about what kind of the protocol you follow for the quality system for the hydrogen. So it's very important we can talk about the hydrogen. First, we can think about what kind of infrastructure. Like you put the AC in the ground, there is no meaning of that. In the AC, there is no meaning of that. Similarly, if you put the like hydrogen, like without any understanding about the safety, understanding about the quality, then system or infrastructure, you cannot use for those. You can talk about these kind of new areas, but it will take 100 years to convert into real application. So it's very important that. So even many years ago, when National Hydrogen Board in India formed, they also follow these strategies. The production, they want to like electrolysis and photolysis, and like chemical method, what you talk about the farming, and the biological method. And storage, they think about the solid storage, liquid storage, and gas storage. And transport, they think about the gas and the liquid. And applications like the transport sector, industrial utilization, and the domestic sector. So why hydrogen? So if you see this slide carefully, because most abundant element of Earth, because I already told hydrogen can be produced from the water, and it's a clean fuel. And third part, if you talk about that, it's a energy density much higher than how then you can able to compare. You can see the comparison with the hydrogen, methane, propane, ethanol, methanol, diesel, or like gasoline, energy 3 times higher than the any fuel. So it's another advantage of that. But I will also talk about what are the critical reasons why hydrogen is not coming in the like the commercial vehicles, that also I will discuss. If you see the lowering the heating value of the hydrogen, self-ignition temperature, if you compare with the CNG and the gasoline, and the like minimum ignition energy required, so safety issue is very important here. And like flame propagation, I will show video also how safety hydrogen, and explosion, and like diffusion coefficient in air, like how much hydrogen can diffuse if you just to leak, and the chemical energy density. So there's many routes already talked about the previous speaker. So a more major focus on the storage. So I will just to pass on these slides, and I will come to storage. So why we'll talk about the storage? Because petroleum is a self-storable because in liquid form, right, at NTP. And talk about the hydrogen gas at NTP, it's lightest gas. Density is very low, like 0.0892 gram per liter, like 7% density of air. So it's so much lighter. If you talk about the hydrogen, it's a bouncing effect, liquid hydrogen in atmosphere. So if you store liquid hydrogen, it will convert to like ortho-para conversion loss. So liquid hydrogen not viable to store. So that's why what is the best way? Like no storage would be the best method. So that's why now people thinking about make the ammonia, just dissociate the hydrogen because the storage capacity is more than 17%. So you can just use directly on board the hydrogen and utilize for the application. So other method we can store in the metal hydride, that we talk about that. And I will little bit talk about the WTC when I attended in Japan. So how we can compare with the Japan regarding this area. So why the metal hydrides, people thinking about like AB5, AB2, or like AB kind of the material. AB means metal, and the one is the metal A, that is the dissociate the hydrogen molecule into atoms, like the nickel or like the iron. Another is like the lanthanum, it can be stored in interstitial sites. So why using the lanthanum? Because it's a rare element. So the F2D block is not filled. So it's easy to make the interstitial voids like octahedral and tetrahedral voids, and easy to hydrogen ion can be. And like similarly, AB2 kind of the alloy can possible, or intermetallics, or like Mg2Ni, many more options there. But why we are talking about the AB5? Because the thermodynamics is much better than any other metal hydride. If you talk about you want to use in the hydrogen vehicles for the converting to petrol vehicles to hydrogen vehicles, then you can utilize the exhaust temperature, and that thermodynamics match with the AB5. So that's why you cannot use for the AB or AB2 or other kind of the intermetallic alloy. Although it's a storage capacity very less, because if you're using this kind of the metal hydride, so it's stored if you just like to gas, if you commercially purchase from the market, the inefficient because storage is like 0.2% to 1 means if you are using a vehicle more than the cylinder, so you cannot use that is practical. So another way is to liquid hydrogen, but already it is expensive. It can be used for the rocket and other missions, but cannot use for the vehicles. So it's a risky ortho-para conversion loss, and ultimately it's very expensive. So third way is to store in metal hydrides, because if you store the hydrogen in metal hydrides, it's an exothermic reaction, and we release the hydrogen from the metal hydrides into thermic reaction. So you can utilize the heat and heating and cooling effect of the metal hydride, and you can use for the not only the vehicle, other purpose, like when you can make the AC. How I will demonstrate some of the application. So that's why we are talking about the metal hydride. But if you talk about the any material, you can say the best one, then you have to explore all the materials, what is possible. So that's why I also work on the carbon nanostructures, because that time there is a projection for the 15 weight% hydrogen in the carbon nanostructures, and other like complex hydride, because 7 to 8 weight% in the case of the sodium malanates and lithium malanates. So people thinking about that direction also. But what we talk about the like the when we talk about the like ionic absorption or like the surface absorption, then the enthalpy then allow for the application. So people talk about the many publications and PhDs, but if you talk about the lithium hydride to put in some device, so they can able to show any demonstration. I'm sure about that. Even fuel cell, there is no required such kind of the hydrogen. They can directly use the cylinder. And you talk about the internal combustion, then you require the metal hydride, because without the enthalpy match with the vehicle exhaust temperature, you cannot use for the application. And hydrogen is a specific for the combustion. Is a very important to understand, because when you talk about the petrol, CNG, or like hydrogen, the compression ratio is very important. So in case of the petrol, very easy to manage, because if you see the compression ratio of the fuel versus region, it's like 1:3. In case of the CNG, 1:8. But in case of the hydrogen, 1:33. So 1:33 to manage in the piston in the cylinder piston. So it's very difficult to manage because liquid form you can just spray from the carburetor for the combustion. But you talk about the gas, then people trying to how they can manage like a lot of the injector are there in the market for the hydrocarbon, which is the higher weight. Same hydrocarbon they are using for the hydrogen, but if it's trying to manage the hydrogen in that way, it may be some back firing chances will be higher because if whole hydrogen is not going to combustion in the like internal combustion, then it's going to accumulate in the chamber. So ultimately, you have to also think about that how we can make the gas injector. If India can make the gas injector, it can be easily to launch the technology. But this is a very critical way where how we can manage the gas to inside the chamber. So that's a real problem for the mechanical engineers. So we have the many IITs and the ICERs. So we can open these kind of the challenges for there, and if they can make, then we will win the market because we already shown this kind of the technology, and we already run the motorcycle. But the realistic way to run, because it's a lightweight, so compact, the blast impact is very less. Because why the fuel molecular weight is required? Because it's also create the impact. If like the gasoline or like petroleum, impact is very high. If you talk about the CNG, then impact is little less with the compared to the petroleum. When you talk about the hydrogen, then the impact is much less than. So you can talk about the intra-city. It can use for the reduce the pardon. So reduce the the carbon content. But if you talk about the speed, then again the problem, if you are not the proper injection, you cannot make the accelerate the hydrogen. So it is required you have to a real injector that can accelerate the hydrogen, not the CNG injector or other gas injector. You can use like butane injector or like the CNG injector, but if you use the hydrogen injector, that will be a great one. So that is the one area where need to discover something that can be used. Another is like how we can detect the unburned hydrogen. So there's a many technique for the thin films. Now is even nanotechnology. So we can make the palladium sensors. So because palladium is a very costly affairs.
Japan is not there.
Pardon? No, I am showing the two ways. This is the experimental areas where the people currently working on the hydrogen, and the Japan is just importing the fuel cell from the Turkey. So Turkey is making the Nephine membrane and the stack. So Japan just to assemble there. So even China now making, but not in the list because the data is that time 2006.
Okay.
We talk about the data now.
It's different.
Yeah, it's a different.
What other Indian companies are doing for Nephine
Pardon?
replacement? Nephine membrane replacement, what we are doing?
In India, people much to just to import. If you are to any institute, the Nephine, I don't think.
I'll show you something.
Yeah, okay, I will be because if we can make the Nephine and the efficient, way to produce the Nephine and the capacity of the protonation is very high, then we can launch the hydrogen by the fuel cell route, not the because internal combustion route you have to follow these kind of the parameters to overcome. If you not overcome the parameters, you cannot be launched in the market because nobody in any company will be in the loss. They will launch the any vehicle. So these are the real open problems. So if you see a scenario in India, because I have the good scenario, I know about the how many people are working in hydrogen. Again, I will say
Previous
Like,
so why India should work just like to make this because time constant you are saying the half an hour. So
it is known that.
so that's why just to switch the main.
Sure.
So they are the major centers where the hydrogen work is going on in India. But again, the data is 2006. So it may be 10 more at the centers.
a lot of
Yeah.
100 more.
Yeah. But again, I will say it may be some like the mushroom kind of the people just started. But the real requirement in India to policy to make very strong and they understand which kind of infrastructure required for hydrogen. There should be some national board that can be safety issues to declare. And there is an infrastructure quality should be there, then only they can work for the hydrogen. Because people work like hydrogen production. So they didn't realize for the real infrastructure required. If you are talking about the application, then again you have to require all kind of infrastructure.
Even just they file the patent and after that they
I mean,
forget. They don't develop. They are not able to develop.
So 1,000 research
Yes.
cannot convert into 1,000 technology.
Right.
1,000 nature papers cannot convert into technology. It may be single without application, but you have the good idea about the industrial application, then you can convert into technology.
And this is what is required.
Yeah, obviously. So that's why, because other areas I'm started because this failure when I learned, then I came to NPL. Then two technology I started. One is the import India from the currency notes for the pigments. So we made with the help of the BNP Devas how they what required they have, and ultimately we match what they imported from the abroad. So similarly in this area, you cannot compromise with anyone. So you have to be what requirement that should be there. Then only can be this is the US the target. So never achieved, because that's why US just closed the hydrogen energy work in 2010. So ultimately again they are start for the hydrogen. Even some examples are there, like Iceland fully converted into hydrogen technology. So if you talk about this scenario, why going to fail? Because just like to publication, if you talk to real problem to work, nobody work. If you are not working the real problem, you can be say like maine banaya. Nobody, if you make a button but without regard to cert, who will going to fix it? So you can make the button, so it can fix any cert. So you have, if you know the requirement for the technology and your work, then only your work is going to success. If you talk about just like to store in some metal hydride or some areas and ultimately I will use, so never we come in that use. So if you really know about some basic idea about the metal hydride, thermodynamics and the vehicle where you are going to use, so ultimately you will going to in application part. Like I can give the best example in thermoelectric. People talk about last many years, right? It's a hot area, new area. Ultimately talk about what will the operating temperature. Then they will say 500 degrees centigrade. Where you will put the 500 degrees centigrade? Ultimately you give the energy and produce the energy. So energy balance is negative. So that's why the thermoelectric hardly come in the market. Similarly in the hydrogen, sometimes when this kind of the area started, the energy balance was negative. Why? That time petroleum was in very low cost petroleum was very high cost, and hydrogen was very to produce is very expensive. So ultimately it's very difficult to match with the petroleum with the hydrogen cost. So people say like that, if you're using the hydrogen, it will be expensive. So now the time has come real, because if you see the petroleum cost is almost that time 2006 3 times higher, almost like 3 times higher.
I slightly differ with any. Go ahead.
Yeah, I will talk later on. So similarly, volumetric storage is also important. So there is many materials that can projected can be stored the hydrogen. But you talk about the dissociation of hydrogen from the metal hydride, it's difficult at the room temperature. So that's why again the question comes. You are saying the 7% in the MgS2, and why you are talking about the AB5? The reason behind that, because the AB5 is the thermodynamics well matched. Second thing is we are not putting any energy to dissolve the hydrogen from the metal hydride. So these things, that's why we are talking about the LNA5. And LNA5, another advantage, if you see the volumetric density in the store in the storage media. So compare the like hydrogen liquid, it's like 4.2 10 to the power 22 Avogadro's numbers. And if you talk about the hydrogen gas and 100 atmosphere, it's like 0.5. And we talk AB, it's like 7.6. So that's why another reason why we are going to intermetallics AB5 type alloy. And now I will talk about, if you compare how it can compare with the gasoline. So if you go with this formula, like 1 gram of hydrogen, like NTP 11.2 liters of hydrogen. So 1 kg of hydrogen, like 11.2 normal meter cube of hydrogen. So 0.2 kg of hydrogen equivalent to 2.2 normal meter of the hydrogen. So it means 1 liter of petrol equivalent to 2.2 normal meter hydrogen. So that's why if you talk about the hydride material, so if you want to 1.58%, so you can calculate like 13 kg of metal hydride required for the 1 liter of petrol. So why this calculation I am showing? Because if suppose you're making a vehicle, so you have required additional 13 kg weight. If you talk about the like 10 kg, like 12 kg, then 200 gram hydrogen can be logged. Similarly, if you talk about 6.5 kg, then it's like, so if you increase the storage capacity. That's why people talk about the MgF2 or other alloys. It may be thermodynamics is not good, but logically they are saying why the high storage capacity is required. So that's why if your storage capacity is higher, then the weight penalty which is coming, the metal hydride going to reduce. So if you compare with the fuel cell, so people using like the fuel cell like just like a stack and just putting the protonate, the hydrogen one side and trying to utilize. So, but the fuel cell, I will also listen carefully our next speaker about the Nephron membrane production in India and what is the cost 2 inch by 2 inch. So then I will realize that which route will be better. But the time when 2006, it was very expensive and nobody in the even DRDO has many projects for the fuel cell and many projects from the IIT Madras, particularly B. Vishwanath and RP Vishwanath, if you know the names, so these people are on the fuel cell leaders. So they also imported from the abroad. So that's why think like that it's very difficult to launch the fuel cell based vehicles, because if 7 or 8 lakhs rupees a two-wheeler, and suppose that time the cost of the two-wheeler is 40,000 rupees, so it can very difficult in the marketing. So that's why that technology not come in the market. But it may be if you can make like the Nephron or some other membrane, because we are the good chemists in India. So, and that can protonate the hydrogen, like the many ferrites they can use, and you can use for the protonation. So material science can be enhanced a lot in 2006 to 2022. So we can try some new materials, and we can try that also in the
technology.
Yes. So how hydrogen can be stored, that for the students, if you put the hydrogen molecule, it dissociates by the nickel, because if you see the electronic configuration of nickel, so it's like the outermost electron is like the unpaired electron. So it's just to virtually transfer the energy to hydrogen molecule and convert it into hydrogen ion. And if you convert it into hydrogen ion, it interlock inside the lattice because of the tetrahedral and octahedral voids inside that. And because the hydrogen ion diameter is less than the void diameter, so that's why it's an interlock. So that's why we are saying the storage in the metal hydride is safe. It's a like exothermic reaction when you take out the hydrogen from the metal. So it's like the endothermic reaction. So it's like the alpha. Storage is alpha plus beta phase, and this is the beta phase when hydrogen is liberated from the metal hydride. So it's like the reversible process. So it's another advantage of that. And if you talk about the sodium alanates, it's not reversible. So again, you have to regenerate. The terminology is different. The chemistry regeneration is again we have to put the energy. But in case of the metal hydride, it's a reversible process.
One more advantage is at low pressure you are able to
store large amount of and another part I want to emphasize. If you see the plateau, pointer is there. This is
Pointer is there.
Okay. So if you see the plateau, like alpha plus beta phase, this plateau is a constant. So if you use for the any application, it's very important, because you cannot use for the alpha phase and you cannot use for the beta phase. The important part we are using for the hydrogen plateau. So now, my opinion, two kind of the things can possible, like double plateau. We have to do the research that can be make the storage in the even AB5 to better and better, because like bimetallic can be composed in a single compound, and plateau can be enhanced, like suppose 4 atmosphere is a plateau, so we can like 4 and 4.5, two kind of the metal hydride we taken and enhance the plateau. So ultimately enhance the storage. Ultimately we reduce the weight and we can use the application. Another way to what in my thinking, because I never seen in the literature, you can make the hydrogen battery. How you can make the hydrogen battery? You can just metal hydride to dissociate hydrogen and lock inside the hydrogen inside the metal. So if you are doing this kind of adsorption, hydrogen valence is negative. So it's like you need not to oxygen taken from the air. You have the one electrode is negative. Another electrode you have to just put like the metal hydride surface. So make the positive electrode, and ultimately you can just to recombine it and create the energy. Like hydrogen density inside the metal hydride with the negative electrode, because hydrogen itself a valence is -1. So you can use like the hydrogen-based battery, like lightest battery you can imagine. But
one more advantage is you can eliminate hydrogen refueling station. You can just cylinders.
Yes, and you can put in the pocket the lightest battery and can use anywhere.
Even for vehicles, you can use.
Yeah, but it's not a very easy task, because when we talk about the this kind of the area, so some of the achievement
is already done actually. I'll share that also.
Okay. Oh yeah. Okay. I will say why it's not possible, and it's done. It's good, but I can say why it's happened. That part also I will share with you.
Sure.
So if you see here, how calculate the enthalpy or entropy by the one-top equation. So if you know the storage capacity, if you know the PC diagram, so you can calculate the enthalpy and entropy and calculate the storage capacity. So what is the advantage? What I talked about that if a commercial cylinder is like 200 bar, it's like big cylinder. When you store in the metal, it's like much smaller. So if you realistic way to understand by the mechanism, right, if you charge the hydrogen, it's a locked in latticeal voids and it's a safe. So if you, it's like a exothermic reaction. And if you feel the heat, it can be when you're charging the hydrogen with metal, it's showing some heat. And if you, that heat can be, again, what the previous speaker said correctly, you can utilize with the exhaust and you try to liberate the hydrogen from the endothermic reaction. So there's several criteria to choose the how you can metal hydride to make, like the capacity, low temperature of the dissociation, like less than 100 degrees centigrade. That's why the magnesium or lithium cannot work. So high kinetics should be there. So that's why physioabsorption is not possible. And like low heat formation. So many criteria I'm listing here. It's very important if you talk about the hydrogen. So now to understand by as a physicist, where the AB2, AB5 or AB, why the storage capacity is fixed, 2.4 cannot be 2.5. So if you see here and you're trying to understand the structure, so all kind of the possible structure, we're trying to do the crystallographic predictions, and ultimately all kind of the voids can possible in the 37 types in AB5, and ultimate maximum voids will be there. It can store 2.4%. So that's why it's in AB5 2.4. Similarly, you can do for the AB2 and AB. So there's many materials we made in the BHU at the time I done my PhD, like more than 19 materials, and we tested like only MMNI Fe kind of the material possible for the this kind of. We can also do the simulation because it's easy to predict the without the experiment. Like if you know the three empirical formula for the concentration of the hydrogen, you can predict the hydrogen capacity. So how you can make this kind of the LOIs? You can, these are the flow diagram. You can just to take a stoichiometric ratio and make the pellet and do RF induction melting, and ultimately you can make this kind of the LOI. So once you can store the hydrogen, you can characterize how you can characterize by XRD, the method you can characterize, and volumetric analysis you can characterize for the hydrogen liberation. And now the PCT Pro is a new setup, more calibrated, so that can use for the hydrogen storage capacity to check. So these are the PCT diagram. So you can understand to storage capacity, if you change the concentration, how it's going to vary. And ultimately, if you know the XRD, so even also you can able to understand if FWHM is going to change. So you can understand hydrogen going inside the lattice. And when hydrogen going inside this, if you see here, there is a lot of cracks. So because the hydrogen going in ionic form and interstitial voids, that's why cracks develop after the hydrogenation. So this is a before hydrogenation, the top one, and the bottom one, the after hydrogenation. So
what is the magnification?
Pardon?
What is the magnification?
So already their magnification is like 10 micron. Yeah. So if you see the particle size, almost like 20 micron, average particle size. So another, like I said, how you can do the PCT diagram. So this is a ledger model. So if you know the PCT, so you can know delta H, delta S, and temperature and concentration. So you can predict the hydrogen capacity experimentally as well as the theoretically. So what is the advantage? Like you have to do the 20 concentration different experiments. So if you know the list and the maximum doping and the middle one, you can able to know the delta H and delta T by that one-top equation, and you can put this ledger model, and you can able to estimate the PCT diagram. So you can see here it's a well matched with the experimental one. So this is one of the area I work for the hydrogen, like metal hydride, how can design, how can simulate, how can we best metal hydride, and what hydrogen can we store. The another area I work for the carbon nanostructures. So because that time a lot of literature was there. So somebody, Baker, projected that the 28% hydrogen is possible in the 1 gram of the carbon nanofiber. So I started with the controversial area, And ultimately, we also work on that area. That time, somebody saying 1 weight%, somebody saying 2 weight%, somebody saying 20 weight%. So why it's happened like that time? Because most of people working for the volumetric analysis. So if you the volumetric analysis, they store the hydrogen inside the still reactor. And if you put the pressure like 120 atmosphere or like 60 atmosphere, and you wait for the hydrogen adsorption. So what's happened? Because different pressure, there's the dead volume is different. But people taking the average dead volume. So pressure is inversely proportional to volume. So if you are using the same dead volume, it means you are incorrect for the storage capacity to measure. So ultimately, this kind of the problem happened many times. Many people reported like that. But we also make those kind of the carbon nanofiber structures. And that time we also get the patent for this setup to make the carbon nanostructure. And this is the real setup. I worked for the VHU at the carbon nanostructure. So because the least cost, you have to make this kind of the setup for the.
Is it coming up? Carbon nano?
Yes, I will show you. We have the patent for that. So ultimately, we store the hydrogen inside the carbon nanostructure, and we seen it produces like the 10 weight% in the carbon nanostructure. But because of the physioabsorption, it's not viable for the any application. So that's why it can be used for the fuel cell electrode, but you cannot use for the any kind of the vehicular application for this kind of material. And second drawback of these materials, the volumetric capacity is very poor because it's lightweight. So it's required again the big cylinder. So even that storage capacity cannot much help. So I will just do quickly to pass because I will cover the third part. And this is the patent. This is the first patent with the Professor O.N. Srivastav on the carbon nanostructures, because we are producing from the calcium carbide. So very cheapest route to convert to carbon. Yes.
8 कब की है?
Pardon?
8
फाइल हमने 2001 में किया था, 6 में ग्रांट हुआ था, मेरी नौकरी मिल गई थी, उसके बाद पेटेंट ग्रांट हुआ।
6 से 22 हो गया, उसका एप्लीकेशन कहाँ का होगा?
हाँ, फ्यूल सेल पे एप्लीकेशन हम लोग कई जगह कर रहे हैं। एक्चुअली CSIR अलग है और BHU का अलग कॉन्सेप्ट है। इंडिया में अभी यूनिवर्सिटी में अगर आप ये बात ये पेटेंट करना और पेटेंट को एक्सप्लॉइट करना, वो केवल CSIR को आता है, बिकॉज दे एवरी ईयर आस्किंग आपने कहाँ बेचा। But BHU just formed the patent their team and.
I just want to raise a question here.
Pardon?
Like, what you think will be the best option? Like hydrogen, you are saying either we are replacing in the IC engine, like in CNG vehicles, or hydrogen fuel cell vehicles versus electrical vehicles. So 3 options are there. Which is the transport sector which should be adopted right now? Because if we invest in one and waste resources, and then we say like Jetrofa will start.
I mean, straightforward answer, and I will just to tell, because coal, you know how much we have, right? And we have many ministers, they are free of energy given to the peoples. And we talk about the electric vehicles, where you're going to charge, because many places you don't have the coal, how you'll produce electricity. So better to get the option where we have the 70% oil reserve, like water reserve in the earth. So that route is the best route. Ultimately, you have to adopt. So that's why electric vehicle, it may be substitutional for few years, but ultimately, if you don't have the electricity, again the problem, because coal is also a reserve in the mines. So ultimately, we cannot depend. I'm saying a technology that you have to think about that cannot depend on anyone. So that kind of thing, and another is like climate. If you talk about
that is, you said, is out of the 2 other ones.
In the current scenario, we have no option other than the electric vehicles. If option, then hydrogen can quickly launch, because India
CNG mix is being tried. No?
So that is the another route like hydrogen. You can just mix 10%, 20%. Like our Prime Minister 2 days ago, they said like if you mix the 2%, we save like 18% the import. So,
but do you think IC engine is not a solution for hydrogen?
No, if you work,
it is IC engine only. CNG is also IC engine.
That's what I am asking you.
No, I am
whether
saying
IC engine is better
IC
or
engine
fuel
is
cell.
working, but you need to make the injector. There is a mechanical 3 sections for the, if you talk about any fuel, like inject in the chamber, and combustion in the chamber, and fully combustion, the energy created. If you have the injector is according to gas, then obviously IC engine work. And
No, but
But-
they will not be doing it like that unless
Yeah.
practically now they are
practically
doing
feasible.
it.
It's feasible.
They
No
have
doubt.
already done. Already now 51% efficiency is coming from hydrogen. In petrol, we are getting only 33% efficiency. With this,
No,
specially designed
ma'am is saying something else. She is saying like this, suppose you have the option electric vehicle, you have the option the hydrogen vehicle.
The electrical you said is
Oh,
out.
okay.
So now let's
Hydrogen
talk
में
about
तीन है
two.
हमारे पास, एक है CNG है, एक है IC इंजन, एक है फ्यूल सेल।
Right.
तो अब इन तीन में सीक्वेंस क्या होनी चाहिए? HCNG पहले कर दें, फिर
If you ask
IC इंजन, फिर ये
if
fuel
you
cell.
ask my experience, I will say cell is the first option.
Yes.
Because why I'm saying about that, in the experience, the protonation of the it's a very easy to understand the efficiency.
And the vehicle which were run by Dr. Srivastava,
Yeah.
they were ICNG.
Yes.
Now we also have got the option in CNG mix. So they must be having the injector. We assume that they have it.
I mean, CNG mix, again, I will say, it may be idea can be differ from the many people's. If you just going to mix the hydrogen with the any hydrocarbon, ultimately what you are going to spray fuel is a liquid. So hydrogen can be create environment for the reduction, but it will not create fully environment what you want to mix hydrogen for that purpose. Like they can reduce the fuel. That fuel is actually not used fully for the combustion. I mean, if you trying to spray the fuel, it may be what required the fuel for the create the energy is higher. So if you mix with the hydrogen, it means that the fuel is going to reduce the hydrocarbon, ultimately reduce the carbon content, right? But how much efficient that content can be controlled, that is not in your hand, because hydrogen is totally as a gaseous mixture with the liquid. Can you convey my? I can
Yeah, I
explain
got
another
it.
way.
It is there, but they change that tuning, fine tune it further, and it is like 70% HC reduction is there, CO reduction, HC reduction is there, and 20% CO2 reduction is there. SPM is reduced.
I can give you a very best example, because as a physicist, my always to nature to debate and try to explain with the model. You can just to make a 3 chambers and make a 3 holes of different diameters, and you try to put the petrol in all 3 and try to push in the hydrogen and make the mixture and try to other hole on the top, and you can check what I'm saying.
But what I'm saying is practical.
No, similarly, similarly it will happen. This is one thing. Second thing, because you didn't use hydrogen, you didn't use the hydrogen, you don't know about the, if you mix with the nozzle, then the carburetor going to strongly going to corrode.
Okay, please go ahead.
Because temperature will be very high.
We discuss later.
So if you
during the team we
Yeah.
can discuss because
so like the storage in carbon nanostructures. So it's if you see the nanofibers, it's like the regular structure. When hydrogen going inside the layered structure, so it make the deformation, and ultimately, if you calculate the area of the deformation, you can justify the 10%. Otherwise, very difficult to understand where it's gone. So that time, these layers basically nothing but but we didn't realize it's a graphene. But in term 4, people just to break through by this cost step, and they understand that if monolayers call it graphene. But we store the hydrogen inside the carbon nanostructure. It's also just to delimitate the layers. So ultimately, there's nothing but the graphene. So we are saying that time the lens-like structure, but ultimately those lens-like structure is later on it's realized as a graphene. So there is a theoretical model also, and then many kind of the carbon nanostructures like nanosprings or like Socker's structures, like to enhance the surface area, so more and more hydrogen can accumulate.
Absorption.
Yeah. So, but ultimately, I mean, another we talk about the sodium aldylates. So already it's like the 2-step process. It's not 1-step process. You cannot get the 7-8% like the 1-step process. So basically, if you talk about the first step, it's sodium aldyl dissociate in the sodium hydride, and then sodium hydride dissociate into hydrogen. So ultimately, it's a very even poor kinetics even. And if we regenerate the sodium aldylates again, it's required the another energy. So what we have done, the intermix with the modified our mixer and make the sodium aldylates with the CNT, and we are trying to improve the kinetics. But again, it's a like physio observation, not improve the kinetics like the metal hydride. If you compare metal hydride, the kinetics in minutes, but if you see here in hours. So because of the enthalpy, if you see, almost like 10 times higher in case of the the metal hydride. So that's why kinetics is very low. So there is many techniques we are trying to make the interface and improve the kinetics, but ultimately we are not in position to put in the like in place of AB5 of alloy. So very quickly I will go. People trying to another technique, because always people thinking something more and more always out of the box. Just to finish very quickly, like
Maybe 2 minutes.
yeah. So I will just then escape that one, aluminum hydride, because I trying this is because our ex-president Professor Abdul Kalam also trying to work on the alanines and he trying to store hydrogen. So that's why, but it's okay. So recently what we've done in metal hydride, when think about the battery, you take out, if you charge the hydrogen with the metal, and take out the air, it's like pyrophoric in nature. It's just to, and you catch fire. So we make a mechanism how we can store the hydrogen in metal hydride and make air stable. So recently we done this work, and what concept we are making that how the plants make the foods. So they make the foods, they're making a membrane of the cellulose. So graphene is also inhalate the hydrogen, and cellulose also inhalate the hydrogen. We make the composite of graphene and the ethyl cellulose, and ultimately we covered it, and ultimately we make the air stable. So that's why the dream can be possible for the hydrogen battery. So that's why I thought like that, because we said like that some people already made. So I've never seen this concept actually. It may be other concept they can make for the, but I'm talking about this concept. So you can see here, if without coating, it's like the catch fire. After coating, there is no catch fire. And normally I'm believe in the beta to in video. So 1 minute, very quickly, I will show. Okay, it's not working. So yeah. So recently we done the MOU with the Hiroshima University. So they are experts in the making the devices. So ultimately our role is to make 2D materials for the hydrogen compressor, so they can be air stable. So they will make the device. So because they have the good facility for the infrastructure for this kind of device, and role already defined here. So these are the few glimpses I can show you how we progress in the hydrogen. Like we taken the motorcycle. Earlier we started to the place of the silencer, we are putting the hydride tank, and then after a few years we are making behind the seat. So it's not risky. Try to understand, because we are putting in the aluminum fins to metal hydride and trying to solid form. So unless and until you can make the pressure difference, hydrogen cannot liberate. Second thing, hydrogen will liberate in plateau. Plateau is very less, like 4 atmosphere or 3 atmosphere. So and it's well matched with the exhaust temperature. So easy to take out hydrogen from the metal hydride. And we demonstrated many places, like also it can be used for the like generator. So a lot of work we done that time. Even you can use the catalytic burning for the cooking. So even like the exothermic, endothermic can be used for the cooling and heating effect, and we can make like AC like 20 degrees centigrade or 50, not like very low, but. And also visited by I think ma'am know about the Ajay Vikram Singh, that time the deputy secretary in the MNRE. So many people say, we also make the in 50 kgs metal hydride. So those kind of the experience. So if you compare with the metal hydride with the, okay. So, okay. So basically some glimpse I can just to put how the Japan is infrastructure for the hydrogen. And many people visited that time to us. So last slide for the young students. Don't bother about the controversies, because they always create the challenge. So just to accept the challenge, convert it to goal. So thank you very much. If any question, I will be happy. Pardon?
Log 9 materials. दो लड़के हैं ना IT के.
हाँ.
और मेटल हाइड्राइड लिए एल्युमिनियम हाइड्राइड से कार चला रहे हैं वो, और मतलब कमर्शियल भी करने वाले हैं. तो
नहीं, वो कब करने वाले हैं? क्योंकि जब आप एलिन बना देते हैं, एलिन यूज होता है, आपको पता है, पेट्रोल प्रोपेलेंट की तरह से रॉकेट में. तो प्रोपेलेंट का जो टेम्परेचर होता है बहुत हाई होता है. आप कैटालिटिक डिसोसिएशन तो कर लिया आपने, कंट्रोल से करेंगे. अब जैसे आप न्यूज पे जाएंगे तो बहुत सारे न्यूज ऐसे हैं. नहीं, आई एम जस्ट टॉकिंग अबाउट द एक्सप्लेनेशन डिटेल. इनसे पहले कुछ लोगों ने कार्बाइड, कैल्शियम कार्बाइड से भी चलाई थी. क्योंकि जब आप कैल्शियम कार्बाइड को पानी में डालेंगे तो रिएक्शन होता है और क्या होता है, एसिटिलीन बनती है और हाइड्रोजन लिबरेट हो जाता है, राइट। तो उससे भी लोग ये एसिटिलीन लिबरेट होती है, उससे भी चलाया था। बट रियल इट इज वाइबल। अगर मान लीजिए 1 करोड़ वैक्यूल चल जाए कैल्शियम कार्बाइड से और एसिटिलीन पूरे एटमॉस्फेयर में फैल जाए, व्हाट विल बी अल्टीमेट। So similarly, if you talk about those kind of the students, so they work for that. But how it is possible like that? Any infrastructure, any quality system, any standard data sheet, how you can claim anything? अगर उनके पास कोई डेटा शीट और आपने देखा है तो आप शेयर कर दीजिए।
I think let me tell you now.
Sir, I have 2 questions for you.
Please.
Question, all that is fine. We are looking for the bulk hydrogen storage. And you don't have to worry about application in the sense, you have to just regenerate it. At the time of the day, when solar energy or electric energy not available, so hydrogen you store when it is available and then utilize it later.
Right.
You're not moving it anywhere.
Right.
That's the solution for industrial applications.
So recently, BRC also projected a project for the land mine storage in hydrogen. So there is a project, the Thermex is a company for the melting the metal alloy, and IIT Guwahati, if you know, the P. Muthu Kumar is working for the. So there is a team like the IIT Mumbai and myself and the P. Muthu Kumar. They are thinking about that kind of the project for the BRC. Because Bhava already asked about the Bhava Atomic Center for the land mine storage. The Pratibha in Mumbai. Yeah, that is possible. Yes.
Actually, already there is a project in US in they are replacing a coal-based thermal power station. They are building adjacent hydrogen storage from solar, and it is underground. They are storing. Yeah.
I think I'll now enter and let's have a 15 minutes break. There'll be hundreds of questions to him. 10 minutes break.
A
Okay.
small video I will show for the students because it's a safety issue,
Yeah,
very
okay.
important.
We will assemble that till 15.
So this is a video for the how hydrogen is much safer than the.
Before we break, I just want to make a comment. You see, we are always talking our country's third or fourth in energy consumption and low in CO2 emissions and all. But when we look at the Environment Conservation Index or SDG index, we are much below. And even in SDGs, even we are below than many of the South Asian countries, not only though we are so much advanced in science and technology compared. So what I'm just saying that we have this small organization which is trying to actually mentor about the scientific solutions of climate change impacts, various impacts. So where it comes into, there are so many dimensions of climate change, the social aspect, science aspect, modeling, technology aspect that is taking action by addressing the challenges, finding the solutions, like hydrogen is one of the solutions. Then there are even so many other dimensions of climate change. Only impacts one can keep on studying this disaster, that. So disaster management is one. So we are focusing on the climate action part mainly, not modeling, but action part of it. And I just want to also say that our people, we feel, our younger generation is the only resource we have, and we are investing our time and money for their future. So that should be the goal for our workshop, should be taken as a goal for the. Thank you.
Give me a good hand.
Yeah.
Excellent.
Sorry, I interrupted you because I was little.
No problem.
When I started,
Yeah.
I also felt that there are hundreds of projects in hydrogen, and so many people are working. So they will just jump over it. But they were only rare, like people who are unique. They came to my this thing, but not everybody. So 100 institutions, there should be no dearth of people interested in hydrogen naturally, and Even this IIT, we get every third day, we get the reminder, but I don't know. So it's really sometimes it depresses, you cannot be, going, you are very, you have given an excellent talk, and you have really given us an opportunity to look into the issues which are concerned. So I'm really thankful to you.
Practical issues.
Practical
Yeah,
issues.
because if you talk
of
about the
storage.
technology, ultimately you have to face.
Oh, yeah.
So if you avoid it, how many years you can avoid? Similarly, like the hydrocell, recently people, talk about the. So what is the hydrocell? Basically, what people have done?
No, nobody avoids it. It happens because of certain constraints.
People,
Financial or
think like that. Okay, I listen many years. Why ultimately hydrogen vehicles are not in the,
And we are doing also so much. It's
Yeah.
not that we are not doing. We are ahead in many things.
Like I can tell
but
you.
it is not.
Yeah, internal combustion. No one has claim here in India. There is the speed of the hydrogen-based internal combustion engines can cross over the 40 kilometers per hour. So if you cannot be economic to cross the minimum speed for the vehicle, how will launch in the market? So then otherwise, some protocols should be there, like hydrogen 3-wheelers or 4-wheelers. Any like Bharat 10 is there for the hydrogen. We are thinking about my last 10 years about the fuel. Any policy is there? Suppose we talk about I have the hydrogen vehicle. I want the number for my number plate. So there is no policy. So what we are thinking? Just like to surface think about the हम अच्छा कुछ बात करते हैं, but never use for that. So straightforward, it may be very tough to.
No, but you can recognize the electrical vehicles in Delhi. You can recognize those, CNG vehicles in Delhi. We can recognize them. There are some indications. I'm not.
So because
it's not that no indication.
Actually, we are not much serious about.
But we didn't go to that level. Proudly, we couldn't go to that level.
Many policy makers, they make the Make in India, Made in India. How many the expert government advisors, they're putting any equipment, their name is there. Can you tell me?
This I don't know.
Right now. This will continue for ages.
Yeah, continue for
Take a break also.
Very
Actually, it takes a lot of time to be present. So if you want to
Hydrogen is lighter than air. It's even lighter than natural gas. Being lighter gives it a safety advantage over other fuels. When gasoline spills, like this water, it puddles and then slowly evaporates into the air. These animations compare a gasoline car and a hydrogen car, both leaking fuel from punctured fuel lines in properly ventilated garages over a 30-minute period. The gasoline vapors are heavier than air and tend to linger in the area of the leak. The presence of a very small amount of these vapors in the air can be ignited. Because hydrogen is lighter than air, a similar leak forms a much smaller flammable. The ignition source would have to be within a foot or two of the leak to cause a fire. If it's detected, the flow of fuel is leak much fuel. The failure of one cylinder with natural gas has shown that a failure of the pressure relief device is extremely rare. The results of such a failure would appear like this. In this demonstration, fuel was purposely leaked and ignited by an electric spark in both a car filled with hydrogen and a car filled with gasoline. The hydrogen tank empties in less than 2 minutes, and the flame goes out with virtually no damage to the vehicle. Inside the rear window, the temperature rose only 30.
और लाइट फ्यूल का मैंने पहले भी बताया कि इंटरनल कंबस्टन में भी स्पीड कम इसीलिए है कि ब्लास्ट इंपैक्ट हाइड्रोजन का क्या है, बहुत कम है ड्यू टू द मास, इसलिए वो एस्केप कर जाएगा, गाड़ी उठा ही नहीं पाएगा तो उड़ेगा कैसे, राइट? No, you can most welcome in NPL. So anytime I can help to any student with the means real solution. I mean, if you are stuck in somewhere, So I will give the real solution to what you can do for the this kind of the fuel and applications. No problem.
Breaking again at 1 o'clock.
Yeah. Could you please come till?
Please call people.
One request which I got from the organizers is that please speak if you want to ask any questions or anything. Please speak on the mic because they are trying to record it. So many of those things haven't been recorded properly because people moved away from the mic. So anyway, we now have the last lecture for this thing. We are lucky that we have Dr. Nand who is an additional Director General in the Fertilizer Association of India. So obviously he's very busy and he has made it, and we're thankful to you for that. He has done his PhD in chemical engineering from the University of Ottawa. He was postdoctoral fellow at the University of USA. Right? He is with the Fertilizer Association of India for the last 35 years. At present, he is Additional Director General, which I've already mentioned. He has been chairman of and member of expert committee and groups of Ministry of Chemicals and Fertilizers, Ministry of Power, Ministry of S&T, etc. So we would like to, without taking much more time, I would like to request him to please address us and tell us about his work. Thank you.
Good afternoon, everyone. Now, I come from a very important segment where hydrogen has a big role, or green hydrogen has a big role. One of the, Gautam Sen mentioned, and these people also mentioned, that one of the ways of storing hydrogen is chemical way, and this ammonia is one of them. Now, ammonia, you all probably aware, is mostly used for making fertilizers. We have three important elements which we call primary nutrients required for our agriculture production, increasing agriculture productivity. And nitrogen is the most prime one. And ammonia is the vehicle for producing or fixing nitrogen in a product which can be applied in the fields, and nitrogen then can be available as a nutrient to the plants. Now, synthesis of ammonia, in the earlier 20th century, to be precise, in 1913, which could be industrially synthesized. It was earlier synthesized also with different chemical reactions, but with nitrogen, hydrogen, starting with nitrogen, hydrogen, it was synthesized industrially in the sense the catalyst was developed, it's a catalytic reaction, and high pressure reactor was developed. At that time, it was synthesized at 600 atmosphere. So it's a high pressure and high temperature, 450 to 500 degrees Celsius. Today, we are synthesizing at 150 atmospheres, around 400, 450 degrees Celsius. It's still a catalyst. And two scientists for that got Nobel Prize, Haber and Bosch. And that's why it's called Haber-Bosch reaction, even today, synthesis of ammonia. In Ludwigshafen, in Germany, and that we consider as a mecca for ammonia people. And one has to wait and see the model which they have preserved for the first few reactors. First few reactors used to fail, almost every day or every 2 days or 3 days. So material of construction, engineering, etc. were important. So one was got for reaction, another one was for developing the high pressure reactor Nobel Prize. And mind you, that no other invention in the history of mankind is so important than synthesis of ammonia on industrial scale. Today, 40 to 50% population will be fed because we could synthesize ammonia and we could make nitrogen application. Our green revolution, scientifically we say 50% increase in the yield of wheat or rice or any other crop is attributed to application of mineral fertilizers. Because I don't know what the background you are, it's a material balance. You just can't keep growing and from something from the nothing. After all, soil is depleted in all these. If there's a virgin soil for 100 years, you have not done anything. If for 3-4 years, it will give you good crop. But if you want that kind of yields, what we call today either organic farming or the natural farming. We were doing natural farming only till early 60s, till the Green Revolution. Our our food grain production was only 60 million tons, 50, 60 million tons. You want to feed today 1.25 billion population. We are producing 318 million tons last year. And of course, part of it we are exporting as well. But that said and done, 180 million tons of ammonia is produced worldwide. And we produce about 10 to 12% of that. We are probably the second largest after only China, the producer of fertilizers, producers of ammonia as well. It's mainly used for fertilizer applications. There are other applications, of course, where you produce nitric acid, ammonium nitrate for explosive purpose and some other chemicals. So we in 23-24 will produce about 19 million tons of ammonia, and we are still deficient, importing about 3 million. We're importing 2.5, which will go to about 3 million tons of imports. So about 22 million tons of ammonia consumption, equivalent to 4 million tons, roughly 4 million tons of hydrogen. Now, what we are talking now is, and it's all, whatever is produced or even whatever we are importing is all produced based using as natural gas. Something also mentioned about efficiency levels. In this industry, we'll take pride that we are at the cutting edge of technology as far as ammonia production is concerned. We are still operating old plants, so they are maybe consuming 10 to 20% more energy. Because remember, here it is a feed is also energy and fuel is also energy. Both is natural gas. I'm not doing anything else. And most of the plants, because they are continuous process plants, they have their own captive power plants. Because our earlier experience of 70s and early 80s was that grid power was highly unreliable. Voltage fluctuations, frequency fluctuations, we are operating 24-hour basis. Today, we don't take any shutdown for years together. That is the deal of technology. Efficiency levels are comparable to best in the world. Still, the benchmark of our old plants and new plants is 2 tons of carbon dioxide per ton of ammonia. So that's where we want to eliminate it. As far as FAI is concerned, we are all networked with our international peers. There is the International Fertilizer Industry Association in Paris, and their technical committee as well as agriculture committee, because fertilizers have to do everything with the agriculture. They merged it together and named it Sustainability Committee. So sustainability in production, in storage, in transportation, and use efficiency. There's another angle I'll just mention. as far as, climate change is concerned, whatever nitrogen is not taken up the plant, and efficiency is only about 40%, sometimes 50%, sometimes even 35%. Average is about 40% in India. So 60% nitrogen, and we call it active nitrogen, escapes to environment, whether it is surface water, whether it is groundwater, whether it is atmosphere as NOx. So United Nations in 2019 adopted a resolution on sustainable nitrogen management in Nairobi in March 2019. And India was one of the initiators of that, the proposers of that resolution. And that resolution, of course, recognizes that agriculture is one of the important areas. Other nitrogen emissions are there even from vehicles, but agriculture is an important area. It is recognized that it is important and vital for food security, but at the same time, we have to manage it in a sustainable manner. In the sense, this 40% use efficiency, which we could easily increase to 60-70%, and this is something to do with what we call is we have a political economy. So pricing of products is controlled by the government of India, and they are controlling urea. 82% of nitrogen application in the sense in India is through urea as a product. So it's being artificially controlled at low price for the farmers, which is about, you will be surprised, is only 15 to 20% of cost of production, or even import. We still import urea. We made 24 million tons last year. We are still import. We may make 30 million tons in another 2 years, but we'll still import. So that is the use aspect, sustainable use aspect. We have to do quite a bit of work. Now, this the 18, 19, or 20 million tons of ammonia, which we are saying, this is there's already, that National Hydrogen Mission. And as a subset of that, there will be green hydrogen mission. And we work with the government because we are, as I said, one of the major hydrogen consumer sector, and other is refineries, which, for desulfurization as well as for hydrocracking of heavy fractions to make lighter fractions. So we are the two large, and these two segments have been identified for green hydrogen consumption. Now, what is this, the policy which we have been part of in formulation? One is the hydrogen production. Now, Government of India in February 2022 has already notified for hydrogen producers, there will not be any transmission charges for interstate transmission of electricity. And then, of course, there are a number of other measures, and for next 25 years. So if you put a hydrogen plant based on renewable energy generated electricity, there are certain concessions given. Idea is that this delivered cost of this energy based on renewable, sources becomes cheaper for a hydrogen producer plant, hydrogen manufacturer, which is basically electrolysis plant. The second segment is that you have to put an electrolysis plant. I'm talking only of mature technologies. I'm not talking of research, what is going on. There are various things are happening, even for synthesis of ammonia, which I'll come to next few minutes. How do you reduce the cost of production of hydrogen? The major cost is the cost of electrolyzers, the capital investment, large capital investment. What are the two costs? The capital investment in electrolyzer and cost of electricity. So electricity, they have already taken the step. So second segment addresses the second part of this policy, which is not out yet, is still in making for quite some time, but we hope it will be out. How do you make this electrolyzer cheaper? So some kind of PLI, what you must have heard, production linked incentives, some kind of incentive for these manufacturers of electrolyzer. Mind you, not manufacturers of hydrogen, but manufacturers of electrolyzers. We hardly has any capacity right now. So the electrolyzer capacity comes within the country So it will be much cheaper than you import electrolyzers, which also internationally is not a very developed, very large industry, because it's still very marginal or fringe industry to generate hydrogen from electrolysis route. So technology not an issue, but how do you bring down the cost? So the second segment will address that. And the third segment for hydrogen cost, green hydrogen cost, not the hydrogen cost, that is still, if there is a gap, for example, I'm importing ammonia. So if I produce ammonia using green hydrogen, whatever is the viability gap funding, so uske liye viability gap funding, we call VGF. So this is the third provision. Till 1 year, now everything is topsy-turvy, upside down. Today, all ammonia which we are producing is based on imported gas, 85% of it. And our cost of production is almost $670, based on $20 per million BTU of natural gas. But still some time ago, it was $10. So it can come down to cost of production, because natural gas is a major cost again. It can come down to $350, $400. At that time, when made this report, green ammonia, the cost estimates were in excess of $800. Now also there are about $750 per ton of ammonia based on green hydrogen. So this is if there is this $750 with all these steps and scaling up, and what they're projecting up to 2030, it will come down. As you see, the cost of hydrogen, that it will come down to 1 kg per, $1 per kg hydrogen. Reliance is also talking about it. So if it can come down to $400 and $450, probably the viability gap for ammonia manufacturers or ammonia consumers will not be there. But these are the three segments. Now, this is one part of the policy, that you make hydrogen available. Now, where does it go? You got to generate demand. So the next part of the policy is that refineries and fertilizer manufacturers will be given obligations to use green hydrogen or green ammonia. It was supposed to start, timetable was supposed to start in 23-24, but it may be a little later. Let's say whatever ammonia you are consuming, so 1% of that to start with, 2%, and then it may go to 20, 30, 25, 30% by 2030 or 2035, and set program up to 2050. So you generate demand. One is you have taken care of upstream supply, and then you generate demand. Similarly for refineries. And third, of course, is CGD, city gas distribution. Mind you, the natural gas consumer, as far as natural gas consumption is concerned in this country, fertilizer is the largest. It's accounting for about 35% of natural gas utilized in the country. Power used to be second or even sometimes first, but because of cost going very high, fertilizers, government is picking up the cost. Farmer is not picking up the cost, so that is not affected. But power generation based on this huge, high cost of thing affected. Now, second, consumer has become, that's why power has been relegated to third place. Second gas is CGD. So there will be obligation for injecting green hydrogen, which is experiment has already started. You must have been hearing, in Assam, Oil India has already done that, started doing that. In one of the CGD systems, they have, produced a very small green hydrogen and injecting into this thing. So these will be three users concerned. Now, what we have said was that hydrogen which we are using for making ammonia, the major segment, as I said, urea is a major, fertilizer made. So hydrogen, this ammonia and urea plants are highly integrated with each other. And carbon dioxide is produced within the process gas, because you are using feed. So where does carbon go? So carbon is finally converted to, it's a multi-stage process, to carbon dioxide. And carbon dioxide is removed from the process gas. It is with hydrogen, nitrogen, and some traces of, carbon monoxide or carbon dioxide. So this carbon dioxide goes to urea to make ammonia plus carbon dioxide react to make urea. So if I get only ammonia, where do I bring from hydrogen, carbon dioxide? If I have green hydrogen, green ammonia, because green ammonia means hydrogen I'm getting, I will put an air separation plant to get nitrogen, because I need nitrogen and hydrogen, synthesis ammonia. But there is no carbon here. So where do I get carbon dioxide? So that is something which is in future will be taken care that how do we wean away the farmers or shift from urea to products like ammonium phosphate, ammonium sulfate, ammonium chloride, ammonium nitrate, no, because of its problems of its storage, explosivity, even whatever we were doing earlier has been stopped because you can't take care of it up to farmers level. We have 2 lakh retailers and 120 million farmers. So ammonium nitrate, no. So how do you shift? So at that time, you put up plants, green ammonia, and produce other products rather than urea. Second thing is, even if you replace partly, you could say the green hydrogen, green ammonia, let us say, then this ammonia plant has to be operated at suboptimal level. And I already mentioned that we are operating at highest efficiency level. So it cannot be your case that you produce ammonia at lesser efficiency and then you use green hydrogen. So that will nullify each other. That other thing is, it has been argued upstream you can inject hydrogen into natural gas before you reform it to carbon dioxide and hydrogen. There also there is a problem of equilibrium because you are injecting product into reactant and that reforming reaction is affected. But so what we have suggested, why I'm mentioning all this major urea production, ammonia may not be touched initially. Initially, you do what we are producing other products where 3 million tons ammonia is going. There is no problem where ammonia is coming from. Out of these 3 million tons, we only indigenous is 5 to 6 million tons because mostly ammonia which is producing going to urea, but there is some surplus ammonia. And 2.5 million tons we are importing. Okay, so we said this is the easier way to replace it, to start with. These are the low-hanging fruits. If you say that some people argued that, okay, carbon dioxide, you can recover from any flue gases, wherever you are burning, any fossil fuel, you can recover. We are also burning in the former. And we have recovered this CO2 from furnace flue gases because methane, the natural gas which we are getting is mainly methane. When you get liquefied, natural gas, because it is imported LNG, all hydrocarbons are extracted. So there is already carbon deficiency. I don't get enough carbon dioxide to convert all ammonia into urea. So one of the ways was that either you sell surplus ammonia, but if there is no market or there is a problem of transportation in the land, then what do? Recycle the synthesis gas. Don't produce ammonia, you go up to synthesis gas level and you recycle, but that's energy penalty. And the third way was that you recover carbon dioxide from those flue gases. And some people have, a number of plants are there, but it's highly uneconomical. This is a solvent-based process basically. And because we are in any case doing carbon dioxide removal, even the processing of natural gas, etc., requires the same technology. So the solvent consumption, etc., found to be very, very expensive. So we said you can do that, but there'll be additional $50, $60 cost per ton urea. We need about 740 kg of carbon dioxide per ton urea. So you're already talking of viability gap funding. You create further viability gap. So it's not going to fly. So let us take off and replace this 3 million tons of ammonia first. Now, where it is required? How do you project this map? Okay. Now, this map is there. Why we have a dedicated map. Sorry to do that. If this much time was there, I could have asked them to mail it. But what I'm saying is, there are 13 locations. Remember, we have a vast coastline. There are 13 locations starting in Gujarat from where the, Sikka or Jamnagar, what you call it. Sikka is the coastal location, about 25 kilometers from Jamnagar. Though you call it refinery in Jamnagar, where SR refinery was also, is not, they have sold it now. And Reliance refinery is also there. There also there's a fertilizer plant. So starting from Sikka, right, going down to Kochi on the west coast, which is Sikka, it is Dahej, it is Bombay, it is it's Goa, and then Mangalore and Kochi. You turn around, going down from Tuticorin, which is very close to Kanyakumari in terms of distance, and then you go up to Chennai and Vishakhapatnam, Kakinada, and then Paradeep and Haldia. Now these are the locations where we are importing ammonia. So you have plenty of choice. Put up anywhere near these hydrogen generation plant, because I said the transmission of electricity, I'll call it green electricity for the moment. The government is taking care, this delivered cost is taken care, and there'll be open access for these hydrogen producers. So you put up a plant there for production of hydrogen as well as production of ammonia. Now you can, to start with, you can, the ammonia plants which are, dedicated, I said, to mention to these are, and some of these locations have urea plants also, but hinterland, there are another 15 locations where we have ammonia urea plants, another 15 locations. So I'm talking about 30 locations. So we are operating now 2,200 tons per day ammonia plants. Now, so we don't talk of that scale. We are talking, you put 100 tons per day, 200 tons per day, and all these ammonia technology suppliers, incidentally, they are all foreigners. They have supplied, we have either plants based on KBR technology or Hallertopso or, a number of others. So that is, let them give me a technology which is economical at 100 and 200 tons per day. That is one. So they are working on that. Second is that if the availability of hydrogen is not, same, because I said we operate right now these plants at 100% load, and 330 days, 365 days a year. Only summer we suffer some efficiency losses because of atmospheric temperature being high, cooling water temperature being slightly higher. Other than that, there's no inefficiency, etc. And these are, we are talking large machines, etc. Compressor, because it's a high temperature reaction, so you need to compress this mixture of hydrogen and nitrogen. So how do you operate these machines at fluctuating load? So that is another thing. Should we have two parallel compressors instead of one for the same capacity, one bigger or one smaller one, and things like that? Though capital investment will increase, so that we can cope with the fluctuating load operation. So one is the scale, other is these fluctuations. In these large plants, we can't do that right now. We have to operate to get the best efficiency. And mind you, the energy penalties are high. You can imagine 1 million BTU is costing you $20 to $25. And I'm talking of, we are operating at, let's say, 28 million BTU per ton ammonia. So these are the two factors which we are telling these ammonia technology suppliers that this is what, and we are bringing together all these people which I just mentioned. There are companies which are putting electrolyzer plants also, one putting it in Bangalore for manufacture of electrolyzer. Another one is planning, they have a joint venture. And all these people we have invited for another bigger seminar at IIT Delhi, and then ammonia manufacturers. And then, of course, storage is also, hydrogen storage we have to address. But this is mainly for industry, hydrogen for industry. We are not talking anything else. And that too, we're mentioning it, process industries. So, and refineries, as I said, and fertilizers will be given the obligation. So we are talking of taking off next year. We are not talking of in a future. We can put 50 tons per day pilot plant first for ammonia, if that is the hydrogen available, or hydrogen pilot plant. In any case, hydrogen manufacturing electrolyzer plants are not scaled, they are modular. In our case, or even for refineries, our scale up is not modular. Larger the plant, you save on capital cost. This because it's not a linear scale up. So that is the stage where we are as far as policy is concerned. Dr. Gupta was very, very concerned about it. Government has still said that it's very soon this policy, as I said, first part was notified, and second and third part hopefully will be notified, but because it has financial implication, first part did not have any financial implication for the exchequer, for the government budget. But second and third, there have to be allocation by the finance ministry, whether it's for PLI or viability gap funding. That's where the government is, these days, anytime it should be notified, this policy should be notified, this obligation will start, whether it's from 23-24 or 24-25. That is something which have to be seen. This is why I mentioned I wanted to give you a picture. This is not something in future. Now we are at it, at the takeoff stage. I use ammonia. Now, as far as ammonia storage is concerned, that is also the title of the thing was. Storage is very, very developed. I mentioned we are storing 30 locations. And another paper which we have published, what is the safety record of this? What are the inspections required? How do we empty a tank? And when do we empty? What are the laws? And the safety record has been excellent, except there are one in 5 years or 6 years, some accident while transferring ammonia, let's say from ship to storage tanks, etc. Other than that, there is nothing which has so far, or within the plants, process plants, there is ammonia pump, which is to pump ammonia to urea reactor at high pressure. So there have been leakages in this ammonia pump, sometimes even during maintenance, because you have not emptied it completely. So there have been some cases. Other than that, we are storing ammonia, as I mentioned, at 30 locations. Now, there are two technologies for ammonia storage. One is that you store at atmospheric temperature. There, then you need a slightly high pressure, 8 bar pressure. And these storage tanks mostly were smaller capacity, anywhere starting from 1,000 tons to 5,000 tons. That is the range. We had we call them hotenosphere, if you must have seen somewhere. These are, and the older plants still have it, but very few of them are left. Now we are talking of large scale storage. Large scale storage means anything exceeding 5,000 tons, right, going up to 20,000 tons. So we have large number of 10,000 ton tanks, which is at atmospheric pressure. There's no high pressure, but minus 33 degrees Celsius. So the refrigeration compressor has to run continuously, whatever, in spite of, these are double walled with insulation, etc. But it's still something is boiled off, the vapors come out, that is compressed again and fed back to this thing. So we have in all these coastal locations, 13 of them I mentioned, they all have these ammonia terminals. We call them ammonia terminals because plant may not be next door. Plant may be 10 kilometers away, 5 kilometers away. Some places we are transferring ammonia through pipelines, other places for road tankers, and one place only through rail tankers from IFCO Kalol to Kandla, which is about 200 distance. That is the arrangement they have within their own the plants. So this is about the storage. So at present, all the storage at atmospheric pressure and minus 33 degrees Celsius. All ships which come, there are again refrigerated ships, and this is ammonia is transferred to in the terminal and then later on transferred to the plant. So that is why, and there's no issue with that. Transportation is also not an issue, except will need additional infrastructure. Storage, there's no issue. Storage infrastructure is already there. As I said, all these locations, there's enough storage infrastructure. And even if you add additional, storage tank, it can be done within 2 years. So that is this thing. Second thing, of course, is we talked about hydrogen storage. So ammonia is also a carrier, can be carrier of hydrogen. It can work as a fuel. We have a presentation from Toyo Engineering. They are working on injecting ammonia for firing in the power plants. They have started already. Second fuel, which we are talking, and you can use it as a fuel anywhere, but as I said, it's a poisonous gas, if you smell it more than 50 ppm. And that's why I'm saying that we have an excellent safety record in spite of making so much ammonia, storing so much ammonia, handling so much ammonia. And the population has come around all the plants. When the plants came 30 years back, there was no population, but there is a population all around the plants. They're talking of as a marine fuel. And there is a separate Ammonia Energy Association. It talks only ammonia as an energy source. So then it's as a marine fuels. The other thing is this calorific value is about 3 times more than hydrogen. It's, as I said, it's it can be liquid at minus 33 degrees Celsius. So the transportation and storage becomes easier compared to hydrogen. Safety record is already proven. So you can use it as a fuel also, whether it is in power plant or anywhere else. But I'm not saying that it can be used in internal combustion engines, but it can be used as fuel many places. But as far as we are concerned, this is our plan to replace this 3 million tons ammonia to start with the green ammonia. We are, of course, a price-sensitive sector in the sense the additional cost. When we talk of viability gap funding, I already mentioned to you that there is already a viability gap of 80 to 85% in case of urea. For other products, also now the international prices have gone through sky, and we are import dependent for other products also. Their government has come back and given additional money that the price to the farmer should remain same. So their viability gap is 60% of the cost. All is being funded by the government. This year's budget, government has already estimates it will be 2.15 lakh crores, what we call fertilizer subsidy. When you read newspapers now, next time, you will see that. It's only next to defense budget of probably government of India. So point I'm making that if there is a viability gap, let us say of 10% or 20%, we already have, the government is already financing such a huge viability gap. Either it can be part of that viability gap itself, or it could be part separately as far as policy is concerned, viability gap for green hydrogen and green ammonia policy, which they will come out. That's all I have to say. Thank you very much.
What are the locations where you intend to use those 3 million tons?
This is a mic.
Location of?
What are the locations you are identifying for that 3 million ton usage?
I mentioned the 13 locations.
It has still not been pointed out because the policy will be out in next month, basically.
Yeah, right. So what I'm saying is there is all these places, there is anywhere from 1 lakh to 3 lakh tons of ammonia per annum required. You give me today, I'll use it today.
Okay.
I'm already importing. The ship is coming. Let's say I have a plant located at Sikka, or let's say I have a plant located at Paradip. Paradip, there are 2 large plants located where the ammonia is 4 to 5 lakh tons per annum. So the ships comes every week. One ship comes of 10,000 tons, 15,000 tons, 20,000 tons ships come for ammonia. So you give me the ammonia, I will first store it and I'll use it whenever I want.
So basically your association and those specific plant owners should agree to use that high cost ammonia.
It's not a question of agree. There'll be obligation under this policy.
No, this obligation will be for everyone. But if association wants only specific plant should...
The policy also is...
Okay.
I don't want to reveal beyond that because it's a policy in making.
Okay.
That is what we have argued at the formulation stage itself.
So it is being considered positively.
That point is being...
Okay.
Hopefully it was taken care earlier.
Okay, thank you. That was my doubt. Yeah.
But so hopefully this will be done. That's what we are mentioned. Inland also, there are 2, 3 or more locations where this can be utilized. It's not that only coastal location, coastal location, mostly coastal location, but inland also are similar plants. Baroda, there is another one.
Actually, last week only there was an announcement that ACME is putting up a big plant of ammonia in Karnataka somewhere.
Yeah, but only thing is because we being a controlled industry, we are not going ahead, at least not planning at this stage, putting up the plant. As a user, yes, as I said, I'm ready. Once obligation.
Right, plant is being put by somebody else.
Let's say I'm taking 200, 300 tons per day ammonia, and there is an obligation to take so much. So in a cluster, I'll take 20 tons per day, another one take.
Right, plant is being put up by Karnataka government. It is financing, and you will get ammonia.
So whosoever puts up,
Yes.
the policy will be, if he is producing green ammonia, I'll be under obligation to take it.
Right.
Yeah.
Instead of the produce like the hydrogen from the ammonia, because it's a good idea because 17% weight percent in the ammonia hydrogen. But why not you can think about that, because you have so many centers, ammonium ion based fuel cell.
Ammonium ion based?
Fuel cell. Directly you can just do ammonium ion one electrode on the fuel cell, and other side is like oxygen you can take from the air. Same the concept like the hydrogen fuel cell.
That's work is going on.
So because you have almost like all the plants in everywhere in the
First of all, please realize that why do you need storage? Even ammonia urea plants which are matched, I still need storage. If there is a problem in ammonia plant, you can't release ammonia anywhere. So storage is required. Storage is not only that I'm because storage is in coastal, because I'm importing, and so I have to store. Ship is not coming every day. What you are saying is there is a direct synthesis of ammonia. That's what you are saying.
No, I am saying like that.
What is the product?
There is a special many materials nowadays, which is atomic thin layers. It's very easy to ammoniate the structure. I mean, you can just to put the ammonia gas, and it will just to replace the halogens and place the ammonium ion. So
Okay.
I am saying like that you can just use a membrane that can just.
But what is the objective? I need ammonia.
Okay, no,
I don't need anything else. If
No,
you want to do something else with ammonia, it's welcome.
No. I am in the I am in the prospect to what this conference or workshop is going on.
I can only mention
Yeah.
that through electrolysis technology, instead of producing hydrogen, there is a technological development which I have not referred to, where you produce directly ammonia.
Right.
That is through fuel cell, not through electrolyzer.
No, my
No,
point.
this is something which is
My
we can exchange later on.
Yeah, my point is different like that. What we are thinking about the hydrogen fuel cell and the membrane is very costly. So we can think about the other ion that can be not the impact on the environment, and that can use for the energy. So that in that respect, I am talking.
That's
And regarding the hydrogen production from the ammonia, there is a many industry in investing the hydrogen. So it's not like the hydrogen production in India is difficult. It's a very easy. Only the thing, once the focus for the fuel, then everybody will think about the store or the make the real use. But in current scenario, because there is no use, like many chlorine industries there,
from
right?
commercial point of view, because I come from industry.
Yeah.
The first application other than fertilizers for ammonia as a fuel will be where you can directly fire ammonia, whether it is power plant or whether it is marine fuel.
Being done through with coal, co-firing with coal. Already it is being
co-firing.
done. Yes.
What you call it, co-firing? Yeah.
Many experiments in material science for the ammonia as a fuel.
Yeah.
The auto combustion.
And one more thing is, with fuel cell also, you put nitrogen and hydrogen, and ammonia is generated.
You get ammonia. That's where the development is taken.
Yeah,
but because this is also this technology at developmental stage. But right now, idea is whatever commercially is available, you put it together, make it viable. This is only matter of economic viability, and go ahead, get ahead. Because once you have an industry which is producing hydrogen, ammonia, or whatever, they can do their own R&D and adopt newer and newer technology for diversification, for newer products, newer methods, and newer applications.
To some extent, because of lower cost of imported ammonia, it is being imported, even if we can produce it in India.
Yeah, this not necessarily, but we do not have enough capacity. We do not have enough natural gas. You put up what we are doing, I said. So we are importing for fertilizers the inputs, as well as our strategy. We are the second largest consumer, and we are the largest importer of commodities, fertilizer-related commodities. So you import gas, make ammonia. You import ammonia. You import ammonium phosphate, which is a product. So, similarly, I don't have a rock phosphate, so I import rock phosphate. I import intermediate phosphoric acid, which is the intermediate chemical. I import the finished product ammonium phosphate. So our strategy is to do all three, whatever options I have, because moment I'm dependent on one, so strategically then I will be exploited. So we are doing everything. For urea, will be almost 90% self-reliance, because though it is again dependent on imported gas, but until last decade there was a priority for fertilizer sector. All indigenous gas, natural gas will be first allocated for making fertilizer, because it's being heavily subsidized. That priority is gone. Now priority is, if at all above, is CGD. Second is this oil and gas extraction, production contracts, which are being signed by the government, now this open acreage lease, licensing, etc. There they have the freedom to auction that natural gas, domestic gas. So now it's a free market. So our dependence on that's why import, it's not that domestic gas is not there, but it's going other places. So our strategy is to do everything possible to meet a large requirement. And you see, because of this, because we had a large capacity, though we had problems of getting some of the inputs recent times, because we are importing from Russia, importing from Ukraine also, plus the other things protected. But we have come out with flying colors as well as our food security is concerned. Half of the nations will starve now. And that is because we have taken care of the inputs as well, fertilizers as well. Weather is not under your control. So whether it will be good bad monsoon or bad monsoon, what is in our control, that you arrange the inputs whichever you can do for agriculture, so the agriculture production doesn't suffer. And
so why then this alternative required to in this program? Because if we are not able to even to fulfill the fertilizer for the farmers, so we think about the other alternative based on the technology we are importing the raw from the abroad. So what is the significance in that context to share?
Today, this is not significance for today's lecture. That's what I have said in last 4 or 5 minutes. What I mentioned was
we should not, confuse to government the policy regarding the hydrogen. Because all data we don't have and expertise, like is a good expertise.
Confuse me. I think we thank Dr. Nand to give us a vast perspective of green ammonia industry use in fertilizer industry and for agriculture. And one question which I have in mind is that how do we use green ammonia as carrier for hydrogen? Is it safe, or because you said that it has 3 times the calorific value than hydrogen, because
per kg. Yeah.
Is it because of the 3 molecules of hydrogen?
Yeah, it's a basic this thing. It's a 4.6 is the GCal per ton of ammonia. That is thermodynamic content of energy content of ammonia. Okay. Hydrogen is much lighter.
So it's how, as a carrier, what kind of transport infrastructure will be?
Yeah, that's why I said that the ammonia large transportation infrastructure has to be developed. Technology is there. It's a matter of cost only. There is no issue with that. And that's why I said from commercial point of view, it will be first, it really is co-fired in the power plants as an energy carrier. As a hydrogen carrier is a later this thing, but it can be cracked again and generate hydrogen and nitrogen again. It's a reverse reaction.
So, but the carrier will be at low temperature. No, is it?
Yeah.
-30 degrees.
Carrier will be at -30. Yeah. Storage will be at -30. These are all refrigerated tankers, whether it is road tank. Small amount of ammonia is sold to chemical manufacturers, whoever has surplus. And maybe there is a business of what, 1 lakh, 2 lakh tons ammonia. So that is also, they are all refrigerated tankers.
Also, shipping infrastructure is already big.
So it's a huge shipping infrastructure there. So, like LNG market, developed. So LNG ships banane mein 4-5 years lagte. But now there are shipyards, whether it is in Korea or somewhere else, where they are making LNG ships. So ammonia ships are being made now for ages. Yeah.
But direct combustion can be made by NOx. So it's to avoid the NOx.
You have to see the NOx emission. Yes. You have to see the.
But you parallelly compare with the hydrogen NOx and the NOx.
Right.
You want to ask?
Yeah, let us have somebody else to speak also.
No, for NOx emission, you have to do two things. One is how do you minimize its emission with the temperature, etc., at what combustion takes place. Second is, of course, end of the pipe treatment, which we in power plants have even now. Yeah.
I think if there are no further question from this group, the two of you could again interact with him during lunchtime and keep on. I think let us give a big hand to Mr. Khan for an excellent lecture. Thank you. I think we have just finished 1:15. That's okay.
Yeah.
It'll be lunch.
So after this is lunch, and before that there is some
Okay, sure.
what? Yeah. Please take. Thank you.
We should do something else also.
No, actually, any new idea came, so I thought to
Yeah,
discuss.
yeah, no, it's a good idea. Thank you.
Yeah.
Thank you for coming. Blessings.
We'll break for lunch.
Green planet.
Yes.
Plant.
मेरे को भी.
Of course.
Oh, thank you. Thank you.
He is a geophysicist and he is working on oil sector, but he is basically physicist. So he vast experience in Reliance industry and in ONGC, of course. So thank you so much
Thank
for
you.
taking out your valuable time, sir. And we
Let's go.
कहाँ जाने का?
And they will come. They said that.
Okay. Shall we start? Ishita, आप शुरू करो. You want to start? You come. Okay.
Good afternoon, all. My name is Monica Banerjee. I am from CSI Simfad. I have just completed my PhD on CBM, shale gas. My topic was petrochemical controls and the gas absorption properties of CBM. So here I actually have attended the workshop on 2015 on CCS with my guide, Dr. Mende. So it's always been a privilege to come here and attend the seminar because there are so many expertise here present. They speak about the hydrogen technology and the energy uses and their in daily to daily life. So it's a good experience. My experience was good here enough to just get knowledge more about that how new technologies can be invented and it can be used in the daily to daily life. Thank you.
What did you learn from the?
Like ma'am, so many people were saying about that ammonia technology and green and blue and different type of green hydrogen, how it is important. So I have to learn more, but still I'm getting some information about that how it can be used like fuel cell. Yes ma'am.
So do you think you have got enough motivation to learn on your own now?
Definitely, sir.
Okay, thank you. That is the spirit.
Yes,
and that is what we wanted.
I have learned I've not have some more knowledge about it, but I've learned something about that. Next workshop I attend and get more knowledge about it.
And in between also study yourself.
Yes, surely, sir.
Okay.
Thank you.
Good afternoon, everyone. Myself, Priyanka Shukla. I am from CSIR Simfar. I have completed my master from BHU, Applied Geology Department, and presently I'm working as a PhD scholar under VM Indesar. I'm very privileged as Malti ma'am gave us opportunity to attend this conference, and also VM Indesar for nominating us. Presently, I'm working on CO2 sequestration and its mineralization, as sir has told already last day. And while preparing for this workshop, I have come to understand the hydrogen and its storage, and also I have learned that how we can generate hydrogen from methane. Thank you.
Magnesium storage you are doing at what depth?
Ma'am, it's presently we will work at laboratory scale at the borehole, and I have taken samples from different depths, and I will try to complete the most depth we can approach.
You are doing underground, not on surface.
Not on surface. I have collected different borehole samples and from different depths and also from different basins.
How you are going to use this information?
This information. Which information from
This hydrogen.
Okay. I think while doing the chemistry part, I can see if I can get something near about hydrogen also.
Actually, what you will come to know, or if you study more,
Yes,
you
sir.
can use this CO2 and this hydrogen to produce CH4 also, methane also.
Okay, the last
through
time
fuel
sir
cell.
has explained
Yes,
that while
yes.
injecting, we are getting a good
Right,
recovery of methane.
right.
So
Even
basically, I am working on a CO2 that is emitted, injected. So we can't leave this to the reservoir. Now it can affect our aquifer, or also during the time of other exploration process, it can be hazardous.
No, I'm giving you something slightly different. You can use this CO2 and the hydrogen produced through different means, combine through fuel cell
Okay.
and generate any other higher gas also, even methane also.
Okay.
So this you can study on your own and try to direct your research towards what market needs. Disconnect is happening, and in inviting the students, we wanted that you should be able to understand that your research should be towards market orientation.
No, sir, CO2 emission is also a big problem. So I want to mineralize that CO2 that we are injecting inside the.
Yeah, that is very good thing you are doing, and that has a
Other
good
than
scope.
that, I will
Yes.
do, but firstly I will focus on my PhD because I need to complete it.
This you need to be avoiding this is just to complete PhD you are doing something, and this is something which you will learn later also, but it is okay.
Every year I have to give my work also, how much I have completed and work plan and everything.
Right. Thank you.
It's Akansha Pandey is left.
Yes, ma'am.
She won't be coming. Okay, she won't be coming.
Dr. Vashni, I have a question to you.
So,
You see, we have been listening and hearing about interface between the research and the acceptability by the industry. Why this has been going on for the last 30, 40 years, but why is not successful in our country? Because this is every building we design, every building we come across, or every forum, they always say that there should be an interface. But what is the reason that is not developing into that level of outside? I have seen that industry is participating very well, but in India it doesn't happen. So I just thought, with your knowledge, that probably you can throw light on this.
yeah, because here people are, you just heard in the last lecture, and they are more oriented towards achieving first the PhD. And while completing the PhD, they don't have anything else to do, just to complete what work they have done. So that orientation has to change, and industry should also finance some of that. Like they should get some incentive to create solution for their requirement. And the topic of the research should come from market, not from choosing by the professor or by the student himself what he is looking to do. So if such interactions happen frequently, and that silo of PhD, silo of industry, silo of financier, silo of different agencies, that record keeping part should get lesser and more towards the PhD should be evaluated towards how fast it can be marketable
Shall I add
to the
something?
solution. Yeah.
Actually, it is happening. It's not that it is not happening. It is quite a bit of things are changing fast, and industry is coming forward, and also government is coming forward to give incentives to industries. Then only this can happen. So if industry is left to private sector, then it may not happen. But when government does the incentive, giving incentive, then it can happen more towards that. And the problem which is also there in the academia sector, because they have certain, as she was saying, there are certain landmarks they have to complete. I mean, they have to do so many publications. So these kind of things have to be little different than what they should be, because they should be given the credit for, because it should not be patent for patent's sake. It should not be publication only, but they should also have to, academia sector has to also move towards commercialization or industry, whatever.
Excuse me, ma'am. I want to add that if I will not submit my work report on time, my scholarship will be get rejected if my project is not completed within an hour. So I can't go for long domains. Now I have to work in the domain within I'm comfortable also. Market purpose is another thing. Even if I will do the research, like the person sitting next to me, she has collected lots of data on CBM in East Bokaro area, and when she gives, nobody is going to talk to her. Like ONGC is doing their exploration there, her record is keeping as it is in the lab. Na? If the company will collaborate with us also, then only we can do these things.
Yes,
and also sometimes we have a threat like you have to publish Q1 Q2 journal only, you have to do this, you will not get scholarship if you are not completing your work within a time limit. So these things, and also the competition, because we also want to reach somewhere after getting PhD. It's not about only completing the PhD.
Good. Dr. Anshuman, you want to say something? Please come this side.
Actually, what we are also proposing, or in some other countries, it is like industry also pays for that. You don't, you are not dependent only on your regular whatever you get research fellowship. Industry also pays to you towards finding the solution.
If there is something link between industry and academy, then it's okay.
Yes.
Otherwise, I'm getting net a fellowship for 5 years only. After 5, we are not getting that. Or the other thing is, sir, like if I'm working in CSI or Simfer, getting my analysis done in different laboratories, it takes money. It also costs time. And even though I'm not getting results sometimes perfect, so I have to redone these things. So there are lots of things that are going inside academy also. We are facing also challenges from step to step. From getting our instrument, every time we call different labs, their instruments are not working. If they are working, we are not getting the slots. These are things. And sometimes it's not affordable for us to get that analysis done on time. So these things are many factors which are affecting us to make us like, okay, I have to complete my PhD on time without focusing on the other
Why
things.
do you keep the data with yourself? Why don't you share it with industry? You have to tell them that you can share your data.
Ma'am, that's what I have felt since 1 year I'm in this field in research. I have seen there is no communication. I don't know who will create this link. I'm not only the person responsible who will going to create this link. I have no idea how to create that link, because once I have attended other conference, the same one of the IIT professor said that we are doing a lot of research and keeping it, and no, if we give this to ONGC, NTPC or whatever, okay, whoever the operators are, if their persons don't even read our report, the work report we provide to them, okay, people on the ground level, they don't read it, they just get it, okay, and if it's economical, like the first lecture also it said, if it is economical, people will read it, do it. If it is not economical to them, they will not going to read it.
Okay, and there is one more solution, that there should be proper transition between academia and industry. Like if I have done PhD, I should get some job in industry, then I am obligated to come back to teaching also for some years. If such transitions, interactions happen more frequently, then this problem can be sorted out to some extent.
I have to add one thing. I've been a professional and I've been busy myself for more than 50 years. And this question is a very general question. And this is a problem of all academicians, that after PhD, what? So you have to be self-motivated with a small group. If you have a small group within your town or within your institutes or within other, then depending too much on your institute or on your boss, it is better if you are self-motivated and also have clearly define your target. I'm telling you on my experience that it is very important that you should have self-goal, and that goal should be very clear to you. It should be, and to achieve that goal, it is very essential that you should be more spread of information and getting more information. So you give your information and get information. You should have a weekly or monthly, you see, a group in which you can discuss for 2-3 hours this thing. Then a lot of things will happen. You'll find that you are not self-coordinate. Right now you are doing and labor. Well, everyone does labor, but motivation and also clearly define your goal and group formation and discussion openly in the group will open more opportunities.
Right, thank you. Please.
Good afternoon to all. I am Dr. Anshuman Gunawat, Assistant Professor, Motilal Nehru College, Delhi University. So, I would like to thank you, and Dr. Alti ma'am, to inviting me and give this opportunity to me. So I am a environmentalist, and I have done my PhD in the agriculture. What is the present and future scenario in the wheat production in the semi-arid region of the Rajasthan. Actually, I am working on the sustainable development goals. Second goal is no hunger. So I am working on the second goal, and now I am thinking about the goal 8, which is affordable energy to all. Affordable energy all. 7 goal. Okay. So we are planning to write some publications on the hydrogen fuel technology, because it is an environment friendly technology. So I am interested in this technology, and because we don't have labs in our college, so the technical work is not possible for us, but we can motivate our students to pursue career in this field. So,
Do you think you can create a lab?
yes, ma'am, but actually there are different provision in our college. Firstly, because environment science department is not a part of in our college, so we can't develop a lab.
Well, it is not, because I remember Dr. Vandana once do lots of plantation on the, so she.
So it's not so I just want to clarify. Add to that what Mr. Sorry. So I just want to clarify what Dr. Anshuman sir was saying. So the department that we have is a very small department right now. So for a department to have a lab, you need to have more number of faculties into the department and more number of students who are enrolled only for that particular course. So like for presently, Delhi University is mandated to teach environment science to every student. So we don't have designated students. In certain colleges now they have started the honors course, and now they are taking dedicated students of environmental sciences. So we are looking forward to that in our college. So most probably, let's see, and like in coming years, maybe we'll be able to see this change in our college also. And if given the chance, we would like to have a lab in our college also, so that we can have some kind of scientific as well as social impact lab, that if we can develop some kind of lab of that sort.
You want to come here and say something?
Okay, I'll come.
You can after him.
I'm here to get some idea about what is the present scenario in the India in the hydrogen fuel production and what are the policies. So I got some idea, and I like the most that discussion after the presentation, because I am going to the on policy making field now.
So you are inspired to get some.
Yes, ma'am. Okay. Thank you, ma'am.
But inspiration doesn't end. You have to work for it. Remember that to get your goal of policy also.
Or maybe I'll come this side and talk. Is it okay? I'm audible. Okay, so I'll come this side.
No.
It's okay, I'll just come, I'll stand over here and speak. So myself, Vandana. It's okay, no problems. So I guess I'm okay. It's okay, ma'am. So myself, Vandana Maurya, and presently I'm teaching in Motilal Nehru College, University of Delhi, and my specialization is environmental sciences and science policy. So I did my PhD from JNU, and my area of specialization was science technology studies. I was basically looking forward towards the policy aspect of various scientific policies that we have in our country, and we were trying to analyze it. We were trying to have more recommendations in terms of energy in the energy sector, and my area of specialization was energy efficiency. So presently, if I talk about this particular workshop that I'm attending from last 2.5 days, it's been quite inspiring for us to understand more about a very emerging field as academicians, where we really don't get a daily update of what is happening in the industry, what is happening in the government in terms of policy making. This is a very good chance for us to learn a lot about what kind of changes which is happening in the industry as well as at the government level. So we get to know a lot about the policies. We got to know a lot about what kind of changes, scientific changes which is happening. For example, I got to know a lot about the various kinds of technologies that is being used to convert different kinds of fuels into the hydrogen energy, and especially with the policy on green hydrogen coming up with the government of India, it's really important for us to know about what exactly is happening in the hydrogen sector if we have to look forward towards the change in the lifestyle in terms of adopting hydrogen in our day-to-day lives. So till now, what I got to know was that hydrogen will be used in coming years. Hydrogen will be used in industry. It will be used in agriculture. It is used in agriculture sector, but as a fuel, hydrogen will be used in industry. It will be used in transport sector, residential sector. We are yet to see what exactly needs to be done. I don't think in the residential sector we will be able to use a lot of hydrogen. But yes, in transport sector, we'll be majorly using it. In terms of adoption of technology, I think there's a lot of work which needs to be done on how we as a public, how we can engage with this new technology, with this new fuel, because at this moment, we don't understand, as a lay public, I'm saying, as a lay public, we really don't understand how this fuel is going to help us. Okay, how this new source of energy is going to help us if we don't think about climate change. So, I'm sure all of you are well aware people who who are concerned about climate change or concerned about environment. That is why we all are here. But there are public who just doesn't know anything about who maybe they know about it. Maybe they are just sidelining it. So for them to accept hydrogen as a fuel or as an energy source, it will be very important for us to engage in the public participation as well as public engagement. So I'm looking forward to that, how we can engage with people. For example, this is the platform where we are engaging with the majorly experts. So how we can engage with the public, general public, so that there will be easy adoption of this technology and or this source of fuel, this source of energy. And moreover, I guess when people, when the public knows about a lot of things, they can always shape the new policies. Because, in our country, we mostly have policies top to down. So what the government is saying, we have to follow. But I guess this is the high time where we should have policies bottom to up. We should know, we should be aware, we all should be engaged in the policy making, and we should tell the government, okay, this is also required. We also need certain kind of other change. So I think public engagement, public participation, having debates, having workshops like this, conferences, this will really help a lot, and especially with this emerging field of hydrogen energy. So thank you so much.
Write a note, each one of you, after you attend this conference, and that note will be with you, so that you really what you have gained out of it and what is your future sort of points which you think and discipline all of us.
I guess that's an interesting idea. And as Anshuman sir was also mentioned, that we are presently collaborating to write a research paper on hydrogen energy, and that is why, like, when Malati ma'am gave us the chance to attend this workshop, we were like, yes, we have to take it. We have to learn more about hydrogen.
I like to add one experience of mine, that I came across new problems and I was not knowing how to do it. But I have known and I worked it out that there are some experts who have done this problem. So I took time and went them. This is what I want in each one of you. The way I did it, and I learned a lot and I implemented that, and that added to my career and that added to my satisfaction. So always never feel shy to go to experts, and they are very kind. If you go, he may be anything, but if you go to an expert, he will give, and if you give time, you find that he will give you something best of his experience in that particular field.
Good evening to all. I am Aarti Bhatia from Universal Public School, TGT Science. And this workshop, I came to know, actually from the starting, I was very much interested to attend it, but I want the school to give me to say that you have to go and then I will attend. But I really wanted to attend this workshop, and really thankful to Malati ma'am as they gave us the opportunity to attend it. And really, my son is there. They are engineer and they also know a lot about hydrogen, and we always have some discussion. But what all the limitations are there in adopting hydrogen as a fuel, that all we came to know from here. And I think that now we have enough knowledge that we can transmit this knowledge. We are going to transmit this knowledge to our students, so that in near future, whenever they are going to for higher studies, so they have the opportunity that they can look into this matter. And I think that the younger brain are more creative and they might think of something new about it. And as you were saying about the residents, I think that if in the residential field also hydrogen can be used, if the hydrogen will produce the electricity, so electricity on in resident we are using electricity everything. So there also.
So I'm sorry, I was talking about in terms of cooking, in terms of
yes, induction or
we will be using
everything.
hydrogen.
I think that resident में जब हम लेते हैं तो we take everything.
Electricity in terms of service it does provide, but I was just talking about as a fuel in the homes, like we'll keep hydrogen in our homes.
Okay,
so that
as
will be
CNG
that
or
will be some-
PNG in that.
LPG, yes, LPG, sorry.
Okay.
Like LPG.
Yeah, LPG or PNG that we are using.
Yes, yes.
Yes, in that matter, but might be their ovens, microwaves, or might be if the hydrogen will be more electricity will be there. Of course, we might be shifting from the PNG or some electrical devices that induction chulas are there that can also then in the near future can be used.
Whole countries use it for heating.
Yes, ma'am.
Actually, both of you are right. There are certain experiments going on. One village in UK is being made for 21 says people are offered to live free. Only hydrogen is used for cooking, heating, cooling, whatever, and for transport in that village. So people are being allowed to use that for some time and experience that. So this thing will percolate and they will, when they go back to their house, they will ask for such things.
And I guess what sir have mentioned, the case study, what sir is saying, it's a very interesting case study. I will surely look into this case study. But this is also a way of public engagement. Like this is how we engage with people, and then we try and demonstrate something to them, and then we once we gain the confidence out of them, then we try and have more or larger diffusion of that technology. So I guess that is how UK is doing. I guess we should, in India also, we have to do something like that.
Even if in the hospitals where we need oxygen, if the electrolysis is done, the hydrogen can be used to produce electricity, and the oxygen also can be used as the condensers that we are requiring for. So for that also means the cost which are there for concentrators can be reduced. If the electrolysis or if they are the
yes,
hydrogen.
already in Noida, one company is using electrolyzers based on electrolysis only, and that is called Exalta. They supplied many electrolyzers at very competitive cost, around 25,000 rupees to Indian public. People were lining up for asking that, but supply was limited because they also don't have that much capacity.
So thanks for inviting us. Good afternoon to all.
Good afternoon to all of you. I am Ikshita Datta from Universal Public School. I am PGT chemistry teacher. I am very highly obliged to be present here to attend this workshop actually. Now, I am personally, as I am from the chemistry background, so I have a huge interest in this field actually. And that from my personal interest, I used to keep in watch of all these things, what the NTPC, GAIL, ONGC, they are doing, what the government policy are coming. So, and in 12th class and 11th class, 2 chapters are there on hydrogen. One chapter is only hydrogen and one chapter is green chemistry, hydrogen economy. So I used to teach many things, electrolysis of the hydrogen, production of hydrogen by the electrolysis process, coal gasification, all these things. But I was always more eager to know in detail, further detailing. And so when I came here and I attend all these things, I listened so many detailing. I got to know different process. There's 5 chemical method we can produce hydrogen, by formic acid, from methane. And also I got to know that, I forgot the name of the professor, by graphene using the solar energy in a biological process, Dr. Ahmed. So we can get the hydrogen as a fuel. And today, and another method is electrolysis is there, obviously. And that is most important. What I was thinking, why the India is so much deficit to produce the hydrogen. So in this workshop, I came to know what the difficulties levels the scientists are facing, and how much we have to grow further actually. And so this is very, very interesting session. And that is hydrogen storage. That was a huge problem, how we could store the hydrogen, aluminum hydride, lithium, aluminum, all these materials can be used different. So I really am very happy to listen all these things. And obviously you have observed, I take all the photographs of the PPT. I'll make a PDF of all these things. And I always, when I used to teach the class, I prefer to beyond the syllabus. So I will take 2-3 sessions with the students, and I will discuss all these things according to my level. And I will try to motivate the student for the further, so they can be motivated. And if 1 to 3 students can be motivated for the research work in this field, I'll be very happy. That is my only motto. And thank you, ma'am. Thank you.
Moreover, you will get YouTube recordings also.
No, I used to observe what the Tata Power is doing, what Reliance in this field, how the government policy, ethanol mixing, blending, renewable process is working.
Can you make the PDF you share with us also?
Okay, 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 thank you. So, this is, I think this is every teacher, they should know in this thing details. Thank you.
Would you like to introduce our speaker? बता दीजिए थोड़ा.
Now, Mr. Rajan Varshney is DGM, Deputy General Manager, NTPC. Now he will be giving his perspectives about the hydrogen production, and he has also coordinating a program with the startups with industries. So I think this, we should all know how the difficulties are faced by the startups when they want to go for industry. And in our country also, the state governments are now announcing. Delhi government has recently said that we want to build up a startup ecosystem. So that issue of what we have been discussing, interfacing industry and academia, will be, to my understanding, will be answered to some extent. So I give the podium to Mr. Rajan Varshney.
Thank you, madam. I'll start my lecture in a while. Let me introduce the method I will follow. I'll start the presentation, and in between I'll try to call the startups also for that specific thing which I am trying to highlight in my presentation. To the extent possible, I'll try to do that and give them some 4, 5 minutes, 6 minutes to speak on that technology and say that what problems they are facing, so that it is more of an interactive session with the people who are connected on the Zoom also. And they are able to put forth their problems as well as what help they require from industry or government or whatever ecosystem to build a faster ecosystem so that their research or inventions can go to market fast. Good afternoon, everyone. Topic which I have chosen in this conference today is slightly different from whatever I have discussed in the course of 2 days, previous and half day today. It is hydrogen from waste. Basically, what is happening is waste is getting generated every day, and lot of waste is simply getting into landfills, and this waste is creating a lot of pollution also. Suppose if we don't treat our organic waste, food waste, methane comes out of it spontaneously after some decomposition within next day or after 48 hours. And that methane pollutes the atmosphere to the extent that it is a 84 times more GHG potent, more greenhouse gas than CO2. So if we can control that methane emission and convert that to hydrogen or use that methane itself, a lot of our energy needs can be met, which we are presently importing. Also, when methane liberates out, it catches fire. It is very this thing in burning gas. So a lot of whenever combustion happens, it is like pollution again. So we have to control this and use our waste to the extent possible, recycle it, upcycle it, or whatever way we can use it. And hydrogen is one of the best ways to do it, more economically sustainable, because hydrogen is a costly gas and we can get a good return out of waste treatment. And in any case, we have to treat our waste. We cannot leave it as it is. So we have to put some expense. That expense can be towards treating the waste and indirectly generating hydrogen. So we can get hydrogen nearly free or at very low cost from waste. Climate change is happening so fast, and human survival is now getting difficult because temperature rises happening very fast. And for India, our 15 cities out of are from the world's top 20 most polluted cities. So in any case, for India, whether GHG is there or not, we have to save our citizens from asthma and other lung related diseases. So we have to tackle our waste and also reduce pollution from various sources, be it energy production, be it automobile, be it industrial, or whatever way. This Deloitte report says if we don't treat our waste, and this climate change is a 11 trillion opportunity, but if we don't treat it and don't control it, it is a 35 trillion risk. So in any case, it is a 46 trillion difference for us. So we have to control this greenhouse gas emission and use it positively towards hydrogen. So urgency is there, and in any case, we have to do it. If we see globally, there is 2 billion tons of waste, and if we can use it towards producing hydrogen, we can produce hydrogen at radically lower system cost, and there will be 90% reduction in emissions and pollutants. And these pollutants are affecting our air, water, and everything. Because when rain happens or the landfill sites, the liquid pollutant called leachate from the waste gets mixed in our underground surface water and pollutes our water. And whenever there is combustion, there are emissions, and then NOx and SOx and other pollutants happen, and they come into our lungs and breathing air, and SPM level becomes high. India has a lot of waste, and MSW is 62 million tons every year. Spare agri waste is 150 million tons. Moreover, there are so many animals. Animal dung is there, sludge, sewage sludge, poultry waste, agroforestry, and other things are happening. From that also, garden forest waste come up, and some energy crops are grown like Napier grass and other things. So we have enough of waste all around the year. At different times of the year, we have different ways, and we can generate enough hydrogen around the year, and that too near the point of use. So the transportation costs also get reduced or eliminated if we generate hydrogen to the extent we require near the point of use. So hydrogen, as we know, is used everywhere. It is a very versatile energy carrier. It is not just we put energy and get equal energy or more energy or less energy out of it. It is versatility also which helps us in using that electricity, which when produced cannot be stored. But if it can be converted to hydrogen, it can be used any time of the year and in any of the use. So that flexibility, versatility is the property which we get through hydrogen conversion of excess electricity. We have seen in Tokyo Olympics, the Tokyo Olympics village was totally hydrogen fed. All vehicles, all heating, cooling, etc. was through hydrogen. All transport was through hydrogen. Similarly, in China Winter Olympics recently in February, everything was on hydrogen based. And in next Olympics also, these things will continue, and these have given enough momentum towards hydrogen economy. I have, as told you, waste goes to landfill and gets burnt or leachate is produced. This is harmful. So what we need is to reimagine the waste and produce hydrogen from it and accept it as a greener solution, because it helps us in GHG reduction, greenhouse gas reduction. It provides us energy security, because most of our energy needs, petrol, gas, etc., we are importing. Even ammonia to some extent we are importing. So all this thing gives us energy security, and side by side tackles our clean, gives us clean air, water and soil, and also waste management gets tackled and imports are cut. Many companies across the world are in this field. Our Indian Plasma Research Institute has developed one plasma gasification technique. Pensaco, US company, it has developed a technology to convert biomass in the absence of oxygen and produces hydrogen and biochar. And this is a patented process. We'll learn more about this in the next in-between presentation during the Zoom. And then other companies, Thermocam Recovery has done gasification for producing hydrogen. Similarly, Standard Hydrogen company, which has tried to mix sulfur with the waste and produce H2S and then hydrogen from it, and then recirculates the sulfur which was used in the first step. Similarly, SGH2 is a company which has enhanced plasma gasification technique, and it produces hydrogen from waste by plasma, using plasma and temperature of around 4,000 degrees. And the better part is they are also making their import from India only. Equipments they are getting manufactured here in India, although it's a US company, US startup. Similarly, there are other companies which are doing it. Shell is doing it in India itself in this IH2 technology. Revelio is again foreign company. Chinook Sciences is again a foreign company. They are doing gasification and pyrolysis. Polycrack is an Indian company which is converting waste to hydrogen. CACH2 is utilizing carbon negative biomass gasification technology to produce hydrogen and biochar. Biochar has a property that it helps in absorbing nutrients and water retention also, and lot of fertility gets improved, and soil is able to absorb more carbon, even many times more carbon. So all these things make it highly carbon negative phenomena. Similarly, this Moat company in US is having a methane pyrolysis technology. They make biomass to heat in limited oxygen environment to around 815 degree and convert it to mixture of gases, producing hydrogen and CO2. And resultant ash is used as fertilizer. Instead of making ammonia and all, here the ash can be used as fertilizer. Hope Resources is using a vacuum reforming process and producing hydrogen from organic waste, and the ash is again additive fertilizer. So these are I've put some companies in this slide. There are many more companies which are doing it and doing it profitably. Pensaco details I have tried to give you some details. They say that their carbon intensity score is -209. So it is a highly carbon negative thing, because the biochar, which is the solid carbon product, it is highly applicable, useful for agriculture, and it can be incorporated as additive in cementitious products, or otherwise the CO2 can be permanently sequestered also. Then there are some other companies which are doing it. Babcock and Wilcox is doing it and producing green hydrogen. And then Government of Ontario and many other governments across the world have released their low carbon hydrogen strategies and are funding those startups. Such things must come to India also. Then this H2 Industries is a US company which is doing some big projects. Two I have shown here. It is a 3 billion plant to convert 4 million tons of organic waste and non-recyclable plastic to 3 lakh tons of hydrogen per year. Roughly, that would have required 4 gigawatt of renewable energy for electrolysis if we go through this much hydrogen through electrolysis. And you can imagine how much land and how much cost of solar panels, etc., would be required, will get occupied if we are doing through electrolysis route. Similarly, in Oman, there is a $1.4 billion plant, and they have signed the agreement for converting 1 million tons of MSW plus some other waste which is in landfills to convert to 67,000 tons of hydrogen per year. The technique involves integrated thermolysis, and this waste heat also from the process is there, which can be used to generate power. So basically, there are different methods to produce hydrogen from waste. One is anaerobic digestion, and then we get biogas and biomethane if we further scrub it further. And from biogas also we can generate hydrogen directly through dry methane reforming, or if we make biomethane, then through steam methane reforming we can generate hydrogen. And the other method is methane splitting. Similarly, we can gasify the waste, and in gasification or in plasma gasification, we have advantage that we don't even need to segregate the waste. Any type of waste can be there, and from that syngas, and then our hydrogen can be generated. Similarly, through pyrolysis of the waste, as we have seen in Pensaco case. And there are other techniques which are called as microbial electrochemical cell, in which microbes are used to decompose the waste in a controlled manner, in a fast manner, and no electricity is required. Rather, we can generate electricity out of that. So this microbial electrochemical and anaerobic digestion, both are through microbes. So these techniques are something which make the hydrogen production much more cheaper and give us carbon credits also. We can earn carbon credits also, and we don't have to use any extra electricity. The green hydrogen through electrolysis route is possible because around 50 units of electricity is required to generate 1 kg of hydrogen. And if we take 10 rupees per unit as the industrial cost of electricity, because we have to use around the clock 24/7 electricity, so that becomes 300 rupees per kg. So you cannot really go down from that cost unless the power cost is lesser, and a lot of water is also used. For 1 kg of water, 9 kg of purified water, 9 liter of purified water is required, and for purification, total water required would be more than 4 times. So nearly 40 liters water per kg of electricity, per kg of hydrogen, and 50 units of electricity per kg of hydrogen. And moreover, that electricity has to come through renewable means. Then if it is through solar, then 4 acre per megawatt electricity is required and land is required. So for that land, it gets occupied. It cannot absorb carbon from the air in natural course and other things. Then there will be PV recycling issues also. And a lot of resources are used during the PV panels also. So in any case, if we use our waste and treat it in a way that we can generate value-added compounds, including hydrogen out of it, that is the best way out. To the extent we can use our waste and to the extent hydrogen required can be produced. Other methods, I'm not saying they should not be used because they are all complementary. To the extent we can produce hydrogen through waste, that should be preferred because it can be in a decentralized manner. Waste is available everywhere and we can produce it in the quantity we require it. So this is first one I have shown you: organic waste, raw biogas, biomethane, and then biohydrogen. The advantages are decentralized hydrogen production can be done, and even in remote off-grid areas also, and even that hydrogen can be filled in vehicles or whatever, tractors and agriculture and whatever we require. Many companies are there which are in the this steam methane reformers they make, and even containerized steam methane reformers, transportable portable reformers through tractor and all. They can be sent to the location where hydrogen is required and methane is available. Biotech USA is doing it. High Gear is doing it, and even in the range of 20 kg to 2 ton per day hydrogen, they are doing it. And some of these companies are, some other companies also including, they are even selling gas as a service. You give them the resources, you call the tank container and get the hydrogen and pay for the hydrogen made by them. We'll see some companies in the startup session and this on-site production of biogas, and from that biogas hydrogen. This I have shown the brief diagram of Biotech, and it says that we can give you at $1.69 per kilo charges for the gas as a service. But this is USA. So in India, if we make it here, we'll be getting it much cheaper. This Hygen quotations, this specs details show that their Hygen 50 model, and on the right side there is a Chinese model of SMR which costs around 8 crore, and its capacity is 500 kg per day of hydrogen. And on the left side, this Hygen model, Hygen 50, is 100 kg per day and it is costing around 7 crores. But my suggestion is, if we go in for Indian manufacturers, in which we see some in the startup session, we can do it in 1 crore or 2 crores, or even less. And then this is through, if we do it through methane splitting, we can get hydrogen and we can cut on the carbon capture cost also. CO2 that is released is not to be captured because it comes under solid carbon itself. And that solid carbon has many uses. Like it can be in the form of tire, it can be used for making tires, plastics, graphite electrodes, carbon nanofibers, even artificial diamonds, and as biochar to increase the fertility of the soil, and even activated carbon to filter the water. So if we do it through methane splitting, and we'll see some companies in the startup session also, they are doing it. So all this is what I'm showing is very current and it is very practically available. Their plants I have shown which are doing plasma methane pyrolysis or methane splitting. This is Monolith USA. This is Hazer Australia. And this get hydrogen at nearly 30 rupees kg. And this is what I'm showing is a lot of energy and resources required if we use make hydrogen through electrolysis route, like the electricity required, the land required, the water required, and specifically the materials like nickel, platinum, iridium, zirconium, yttrium, etc. So in this case, the minimum cost of green hydrogen comes out to be around 300 rupees per kg. This is a table comparing various technologies and their maturity level. So if we see steam methane reforming is quite mature technology. This maturity level is 9 and cost is around 110, but it is giving us gray hydrogen. For 1 ton of hydrogen produced, 10 tons of carbon dioxide gets produced. In coal gasification, again, the cost is high and even 20 tons carbon dioxide get released for 1 ton of hydrogen. For anaerobic digestion method, the cost I have already told you is 30 rupees and SMR is quite mature technology. Water electrolysis, again, mature technology, but the cost comes around 300 rupees. In pyrolysis or methane pyrolysis thing, the technology is still maturing to some extent, but reasonably mature, and the cost is around 140 rupees per kg. But if we take into account the carbon which we get generated and CO2 is not required to be captured as it gets captured in the carbon, and many carbon products get good prices. Like carbon black for tires, if it is properly made with the right properties, it can be sold at 100 rupees per kg or even more. So this cost can be compensated to some extent. Then this microbial electrolysis, I'll give some more details in the next slides. And this can be a good one, but it is in the TRL5 level and cost comes around 40 rupees per kg. And this is microbial electrolysis through microbes, waste eating microbes. They produce hydrogen out of eating waste. And these are some of the advantages. And the rate comes around 40 rupees per kg if we can scale it up to 50 ton per day plant. But this is presently patented technology, and it is what they have is a proof of concept of 5 kg per day. And as we already know that many imported and costly materials, rare materials are required for electrolysis. So again, if we go for waste to hydrogen, it can be a boon to our country because we don't produce those materials here. It is clear that H2 has minimal import hydrogen economy. Why we should adopt is because it has minimum imported material content as a whole also. Because fuel cell also and electrolyzer also have very little imported content of rare materials as compared to electric vehicles, which uses battery and other things. So in any case, hydrogen is, as Dr. Gupta also said in the morning, hydrogen is preferable for India because we don't have those materials. And even if we, wherever they are, extraction of them, these materials creates a lot of pollution. And this is, I am pictured with the Toyota Mirai. And I had been instrumental in getting these notification of HCNG and fuel cell safety standards, which were released in, amendments were given in, notifications were released on 23rd September and 25th September respectively. And now Mr. Nitin Gadkari is having a Toyota Mirai, and it was launched on 16 March. And then this HCNG is also a good transport fuel. This is 18% hydrogen in CNG, and 50 buses were run after that notification on 23rd September. From 1st October, they were run, or maybe around 10th October for 6 months. And the third-party test results show that CO level was minus 77%. Carbon dioxide mitigation was this much. Total hydrocarbon were reduced, as put in Supreme Court report, it was 15% reduction. And efficiency was plus 4.77%, increased and not much cost, not any cost was there on the bus side. Same CNG cylinder and same engine, same everything, but only tuning was changed to suit the HCNG. And on the pump side, to produce HCNG, autothermal reforming of natural gas was made. So no extra compressor and everything, anything was there. Only autothermal reforming was adopted, which gave the mixture as 18% HCNG. Then all this hydrogen and blending can be used for cleaning the power. Like in the comments section just before the session, people were saying how hydrogen can be used for generating electricity. So it can be used, and it is being used in the starting pilot projects in different countries, in China, Canada, US. And even co-firing with coal can be done. And all this will reduce pollution to large extent. As we have seen, HCNG reduction pollution was 77%. Similarly, this Uta power plant is being planned for 100% hydrogen from 2045 and initially 30% hydrogen in the gas turbines from 2025. And that hydrogen again will be green hydrogen. So if we see strengths from waste to hydrogen, we have lot many strengths and lot many benefits. Weaknesses, people don't understand that it is green hydrogen, and so they don't get that much funding and support, and no level playing field is there as on date, but scenario is changing. Then we are, even if we have the Indian technology, again, we are not getting it to the market faster, and we are importing those other technologies developed elsewhere. Opportunities are enough. We want to become self-dependent. Atmanirbhar Bharat potential is very high, and the distributed concept is there. Waste is available everywhere, and whatever hydrogen we require, we can produce that one there. Gestation period is very small. Hydrogen costs are really attractive, and threats are new technologies may come, and then these investment may go down, but still there is a lot of scope. Stakeholder engagement is there. Society is demanding cleaner technology, like people were asking how our homes can be clean with cleaner energy and all. Entrepreneurs are also fast developing those technologies and trying to scale up fast, as we will see in the next session also. Politicians are also putting pressure, governments are putting pressure, and there even many governments across the world have signed net zero strategies, funding strategies, and the financial markets also have realized that hydrogen is going to stay here. They have understood the fact that they have to finance hydrogen projects, even if they are new, but they will be there and they are an asset. So we can always have some policy recommendations, like we should have certified carbon intensity instead of different colors of hydrogen. There should be a verification authority, and the whole process should give us how much carbon negative it is or how much carbon positive it is. So if that classification is done, then carbon finance market can help in developing those technologies which are more carbon negative, and no extra funding will be required. That carbon mechanism will be able to fund. Similarly, policies supporting decentralized waste to hydrogen should be there, and they should encourage that waste, instead of getting accumulated, should be treated fast. So in short, we can say that hydrogen from waste has many advantages, can be stored and used when needed. Major components can be manufactured in India, lower capital investment, decentralized hydrogen production can be done near the point of use. Rural microgrids, remote places also can be electrified very easily, and we can get 24/7 clean electricity and energy supplies needs. So summing up, hydrogen waste from is a very good key driver, and it supports energy economy and environment, meeting the requirements of grid stability, energy storage, transport and utilization in microgrids. Costs can be very low. Typically, even at 30 rupees per kg, we can get this hydrogen if we incorporate the cost of the byproducts. Hydrogen from waste is greener than green, so-called green, which is electrolysis, but it affects so many land and other materials and recycling and other things, and a lot of electricity is required. And it can be as green as the electricity, but at present, Indian grid is having more than 80% coal-based electricity. So rather it is more green because it also prevents contamination of soil, water and air, and mitigates greenhouse gas emission and returns carbon to the soil. This helps in improving fertility, reducing fertilizer usage. If we can improve soil carbon, fertilizer needs are tremendously cut. Even 70-80% less fertilizer is required. And since this has the property of water retention and oil and other vegetation, so it prevents soil erosion also, and even landslides to some extent. All SDG goals can be addressed, some of them directly, some of them indirectly, through waste to hydrogen. So in conclusion, waste to hydrogen is greener than green. Green hydrogen is multi-decade opportunity. Green hydrogen can integrate RE sustainably, because if hydrogen can be produced cheaper, then it can be used during the time solar and wind energy is not there to supplement that, say in cloudy atmosphere or during the nights. And it can have a good microgrids, 24/7 electricity supply through green means. Additional benefits: cleaner environment, avoid methane flaring, waste treatments, because even from waste sludge also, sewage sludge also, we can generate methane and then hydrogen. Or even methane can be used directly in some types of fuel cells to produce electricity. So we can free our prime lands, which is getting logged by landfills, more jobs, lesser migration, because a lot of 24/7 electricity and related following facilities can get developed during this regime in the villages also. So there will be lesser migration. People will be able to enjoy same urban benefits at the village level, lesser imports and higher exports. Because if we can produce low carbon steel, green ammonia, green hydrogen, we can export them. Instead of getting petrol from Gulf countries, we would be net exporter of hydrogen if we can do it properly. So planet, people and prosperity, everything gets addressed. This is a triple P problem, triple P benefit, and it is a win-win for all. Thank you. So we'll take questions after the session of startups. They have joined. Just show how many participants are there in the Zoom call. So welcome from India. I will first invite Mr. Gerald Hollins, CEO of Hydroloop, to present on a green electricity based concept of using ocean OECD and how it can be used to give us green hydrogen continuously and cheaper round the clock green electricity at affordable prices. Welcome, Mr. Gerald.
How do you do? I may not agree with the affordable price piece of it, but you are correct on green hydrogen, green power providing green hydrogen 24/7. I'm going to screen share a document that I have prepared for this
Actually, I won't be able to share that right now because I have not downloaded it. You can just speak for some time, and if you can share it from your end, it would be good.
Okay, I'll see if I can screen share this. Can you see it?
Yes, it is coming.
Okay. So we've been pursuing a project in India now for several months, and it involves converting ocean heat to electrons and using those electrons in a number of different applications, be it green hydrogen, green ammonia, desalinization, wastewater treatment, green steel, green alloys. This platform is also a fish farm, so it's producing fish. It has multiple applications. The model we developed is 500. It's a generic model. We're using the number 500 gigawatts, but all the equations that we apply are linear, and we compared our technology, or we compared the project side by side with solar going to storage and then back to green hydrogen. So we have some data here. I talked about what happens when you put a 500 gigawatt solar plant up, and atmospherically, there are things that happen that take place when you put up large scale solar. And I'm just going to walk you through that for a moment. The assumption is that if you're putting up a 500 gigawatt plant, you're actually going to be putting up 1,000 megawatts. And the reason for that is you want to go 2x, and in some cases 3x on the amount of power you put up for solar. And there's a number of reasons why you do that. I won't get into why that is. We could talk about that another time, but essentially the side-by-side that we're looking at is a 500 gigawatt project with 1,000 gigawatt solar installed. And solar takes up roughly 5 acres per megawatt. That means that a 500 gigawatt project would require 5 million acres of land. Each square meter can produce approximately, I think, 6.2 kilowatt hours per square meter. And the actual radiant heat that is absorbed and rejected is somewhere on the order of 1.8 kilowatt hours per day. On a 1 million megawatt project, you're looking at somewhere on the order of 37 million megawatt hours of thermal energy that are released back into the environment. What happens when you put that much heat back into the environment, you create what's called a solar chimney. A solar chimney is where you superheat a surface, and that surface reheats, and sends heat back up in the troposphere. So there are multiple impacts to doing that. One of the impacts is you start to, you're using that heat is applied to what's called the water cycle. The water cycle is evaporation of water, and water is the force in weather today. So all the extreme weather we're experiencing today is partially carbon, but majority water vapor. So if you're pumping heat into the environment, you're creating more evaporation, and more evaporation is actually driving climate change. So what we're telling you here is you put up a very large solar facility, and you're actually going to be driving climate change instead of stopping climate change because of the heat that you put back into the environment. Our team put together a document that explains side by side what storage looks like on from a green hydrogen standpoint. So I won't spend a lot of time discussing this, but as you can see, we have economies of scale at X number of gigawatts. So we start out at a higher number, approximately 580 rupees per kilogram of hydrogen, and we end up with 290 rupees per kilogram, whereas a solar storage system is roughly 490 rupees per kilogram. We have a project model that we're presenting, and that project model involves two projects, one on the east side of India, the other on the west side of India. One into Mumbai, the other into Chennai. So the approach we're using is to install zero emissions, green power, and distribution infrastructure on 2 urban centers in India. The primary use of said power shall be green hydrogen production. If we just use our power project for green hydrogen, we feel this is not a viable project. This project must take on more than just one energy use. These are the categories of products and applications that we feel would make a OTEC project viable: green hydrogen, green water production, wastewater services, ammonia production, green ammonia bunkering, green steel production, green alloys, powering green data centers, fish production, and it also is a ocean plastic cleanup platform. So that's really it in a nutshell. If you have, this is our layout for Mumbai. This is the layout for Chennai, and offshore Chennai. This is what the project would look like. We don't give specifics on the actual dynamics, dimensions of the project, but this is where it would sit. We would be sitting the project roughly approximately 60 kilometers off the coast of Chennai to produce power. So it's beyond the line of sight. You have virtually no land impact for this project, whereas solar, you would take up approximately, for the same power output, you would take up approximately approximately 5 million square acres, whereas this project virtually takes up no land other than the substations that will be installed. So that's the presentation. And anyone has any questions?
Thank you, Gerald. Is anyone having any question on OECD? Thank you. We don't have any questions.
Very good. Very good.
Great.
Okay.
Thanks a lot.
Thank you. Thank you.
Can I now invite Ms. Sebel Huang, Chairwoman ROG H2? Yeah, please.
I use my CEO's laptop. I'm sorry, it's Florian von Hofen.
Okay. Can you present yourself or should I share the screen?
I have not tried. Can you do that for me?
Yeah.
Thank you so much.
Just a second, we are sharing.
Thank you. First of all, good afternoon. It's a pleasure to be here to introduce the evolution of our technology to achieve net zero emissions. And now we are waiting for the charts.
This is the technology where we can directly convert biogas to hydrogen and other green things like green nitrogen and all, from which we can make ammonia also.
Yes, thank you. In 2006, after seeing the movie of Inconvenience Truth presented by Vice President Al Gore, I decided to invest in new technologies which can reduce and remove greenhouse gas emissions. So in early 2015, I discovered a new patented technology at Graz University of Graz University of Technology in Austria, which had the potential to produce high purity hydrogen directly from biogas, defined as zero emission, required less capex and opex comparing to traditional process. So I bought this patent, founded Rouge H2 Engineering, and started many activities to validate and optimize the technology with reputable partners. Next, please. Next chart, please. In 2021, the world's first high purity hydrogen directly from biogas was realized in Austria with TU Graz and the local biogas plant association. Next, please. In 2022, the world's first high purity hydrogen directly from landfill gas was realized since February this year at a European funded site in Cologne area in Germany, with a research center supported by Technology, Arts, Science of University of Cologne. Next next page, sorry. So at this moment, we are working hard on optimizing the technology and also working on validating the upcoming technology. We believe that we will have better results within 1 month. And this technology is based on chemical looping. So on the left-hand side, you can see that it was completed in 2019. And we have been running it for more than 2.5 years. And at that time, we did not capture the CO2 from the gas mixture. And because we realized that we can have very pure CO2 spring from this process. So we modified and improved our process control system and started to capture the high purity CO2, produce hydrogen and high purity nitrogen 2 years ago. But now we want to increase the rate of carbon capture up to 99%. Yeah. Okay, next, please. And this is analysis and also small tests we have done with our partner. And you can see on the left-hand side is a traditional wood gas gasification, wood waste gasification process. And on the right-hand side is the same wood waste gasification process, but we replace the electricity generation into the hydrogen production. So we will produce 13 kilogram hydrogen per hour, and the capture at that time is 15 kilogram CO2 per kilogram hydrogen, and 16 kilogram nitrogen per kilogram of hydrogen. But this process we will improve and will present within 1 month, which we can capture more than 20 kilogram CO2 and around 20 kilogram nitrogen. And for this process, we also produce biochar, and it's also carbon negative. And the CO2 can be captured and stored as a negative emission process, or be utilized in other process for producing chemical or fertilizers. Next page, please. And this is ongoing projects we are working right now. We have a project for the Winter Olympic in Italy, 2026, and in Germany, in UK, in Indonesia, and Thailand. It's many waste wood gasification from agricultural and forestry waste. And the topology is very simple, because we use the gasified syngas, and then our core technology is, as presented previously, is a chemical looping process inside one reactor. And with this one reactor, we can reduce the other additional process to capture the CO2. This is called pre-combustion capture. And we produce high purity biohydrogen up to 99.997% purity, and pure nitrogen. This pure nitrogen and H2 can produce renewable ammonia. And after the ammonia, we can use part of the CO2 we captured to produce green urea or fertilizers. Yeah. Next page, please. And for the reaching the net zero goal, we need to speed up and scale up, and our technology can help in all the sectors to reach net zero emissions, including the BCCS, bioenergy, carbon capture and storage, and fossil fuel based CO2 removal, hydrogen production, and electrification, because of course, the hydrogen we produced can generate electricity by hydrogen gas turbine or the fuel cells. And because our system is very simple and without electricity to produce high purity hydrogen, so the energy efficiency is largely improved. And next page, please. And let us take a look at the greenhouse gas emissions by sector in India. And let us see the first sector and the second sector. We believe that with our technology, the first sector and the electricity and the heat, and second sector agriculture, we can help to reduce by 50% to 60% respectively in India. Next page, please. And let's take at the CO2 emissions by fuel type in India. And to reach the net zero, and we take the net zero pathway, we believe that the low carbon H2 without any colors, only to look at the CO2 intensity, with our technology, with carbon capture and storage based polygeneration from integrated gasification combined cycle, will help a lot to reach the net zero in India. Next page, please. And this is with a cost estimation provided by International Energy Agency and the Department of Energy of the United States. You can see that with coal and biomass gasification, with CCS in the middle, the CO2 intensity can reach 0 emissions, and the cost will be around 1.5 to 2 euro per kilogram. And I believe this in India can achieve this target in the near future with our technology. And next page, please. And this is the introduction of our team. And I have been the angel investor since 1998, and with many experiences in professional equipment and construction, engineering, and so on. And we have Mr. Howard Beer as our advisory. On our advisory board, he is the head of office of European Biochar Association, and we also have very experienced safety experts with us. Next page.
Thank you, madam, for sharing all these details. It has been really nice. People are appreciating your technology. Let us hope in India also we'll get some pilot, maybe funding from your country.
Thank you.
Let us explore that. Yeah, thank you.
Thank you.
Do we have Mr. Siddharth Mayur? Siddharth, are you there?
Hello.
Okay.
Hello. Am I audible?
Yeah. Yes, Siddharth, you are audible. You can, I would just like to say that you are CEO of and founder of H2E. H2E is doing tremendous work here in electrolyzers and fuel cells and even power to chemicals, fuels. So please introduce about what you are doing here and what facilities or what support you require. Your inventions should go to market faster from government, from industry. Let us have this such a perspective which will be useful for us to put it to government and every agencies. Thank you.
Thank you, Rajan ji, and hello everyone. My sincere apologies for being late. I had some problem with my computer, and for some reason it was not rebooting. So I'm really sorry about this. Am I audible to everyone?
Yes.
Hello?
Yes, you are very much audible.
Okay, wonderful. So I think without wasting much time, I will just put my screen on and I will start up with my presentation.
You will have 7 to 8 minutes. So
yes,
even if,
visible?
Yes, it is visible.
Okay, great.
Yeah. Am I audible to you guys?
Yes.
Okay, Siddharth, this is Parimal here, if you remember me.
Yes. Of course I do.
Can I take 1 minute, please?
Sure, sir. Sure.
Thank you so much. I wanted to go, Mr. Rajan, can you, am I audible to you, Mr. Rajan?
Yes, you are audible, Parimal.
Yeah, so you gave sessions to others and you didn't give it to Florine.
I really apologize. What you want, please tell.
Yeah, so she gave some cost numbers and we would like to probe that a little.
After the presentations get over, if she is there,
that's fine. But you can inform her in the meeting.
Sure.
Okay,
Or you can email me the query. I can tell her. Yeah.
No, I just have to ask her, how did she arrive to those cost numbers? And how are they going to, optimize those cost numbers?
Okay,
That's all.
we'll solve your query.
Sorry, Siddharth, carry on.
Okay. Good afternoon. Let me just give you a very brief background about H2E. We are a fuel cell and electrolyzer company. We build solid oxide fuel cells and solid oxide electrolyzers. We also are into AEM and alkaline electrolyzer space. We've been working on this for the last 11 years now. And I'm just going to run you through some of our experiences or some of the technologies that we work on. This is a historical picture for us because this is the first time a green hydrogen plant was commissioned in India. This happened on 20th of April, 2022. And I've just borrowed from Neil Armstrong's statement when he said that it's a small step for man, but a giant leap for mankind. But in our case, it was a giant leap for climate change in India. And this definitely was a significant and an important step. So this is a project in Assam, in a place called Jorhat, where we are producing green hydrogen using electrolyzers and solar electricity. And we are also blending that green hydrogen with natural gas. We are currently running a project where we are trying to identify different use cases of the blended fuel, whether it is into vehicular side or it is getting into the city gas distribution network, bringing it to every home. The whole idea is to start working towards or marching towards that net zero target that we have all set up for ourselves and also for the country. India, for instance, has set up a target to achieve energy independence by 2047. And that in itself is a daunting task because India today imports $160 billion worth of energy from the world. So almost 86% of our crude is coming from outside of India, and 56% of the gas comes from outside India. So for us to reverse that 160 billion and go to zero by 2047 is a big task, and technologies that we are working on and you're going to see in the coming slides are going to be important for that. And 2070 is the second date that India has decided to go net zero. So we are all working towards these steps. And at the same time, the climate catastrophe also is that we have to sacrifice our growth if we want to save the planet. But in case of India, the growth is we've just started growing as a country. So saving the planet, but also saving the economy. I think technologies like hydrogen or technologies like bio-waste or bio-CNG are very important to bridge this or to solve this dilemma. I will run through this slide. This is more on how the energy transition is happening from the fossil-based electricity moving into the hydrogen economy, where we are talking about hydrogen as a dominant molecule, and then we are talking about powerful fuels. When I say powerful fuels, these are e-fuels made out of the hydrogen molecule, like ammonia, methanol, kerosene, and which can then work on hard-to-abate sectors like aviation, marine, industries on the ground. So when I talk about India's net zero pathway, as I said earlier, we're looking at renewables, waste to wealth, energy storage, power to X, and green hydrogen. These are going to be the key ingredients towards achieving the net zero. And on this slide, I think this describes a lot about how the whole hydrogen economy is going to come in and what are the things that are going to be affected from the hydrogen economy. A lot of us who are present today already know about this, and I will not go into detail. If there are any specific questions, I'll be more than happy to answer those. So when I was talking about the different ingredients on my previous slides, one thing that we need to also look for is that 6.5 million people died worldwide due to COVID-19. And believe you me, the world was, for the first time, I think after 9/11 is when the world came together as one. We actually had a lockdown. The world had a complete lockdown for more than 100 days. But due to climate change, there are 5 million deaths per year. Nobody talks about that. So that's never been an alarming subject. And that brings me to a concept here, which I want to share with everyone. that can we all get together, technologists, academicians, industrialists, financiers, come together to build a vaccine for climate change, because the earth is also suffering. And one of the key ingredients to this vaccine is going to be hydrogen, and then hydrogen used with the fuel cell or hydrogen used with different technologies, which can be probably be the candidate for making of this vaccine. In India, these are kind of key drivers. I will just move quickly on this. Key ingredients for a vaccine, which I called as a climate shield vaccine. We have Covishield in India. Most of us have taken that. Is renewable power, which is very important. Solar, wind, hydro, geothermal. Water is again an important ingredient. Not many of us talk about it, but if you're looking at a bio-waste process or electrolyzer process, water is other than electricity, it is a key ingredient. And if you're looking at India as in context, we have a big problem of drinking water. And if you're going to tell the people that we're going to sacrifice drinking water to produce hydrogen, they would rather let the climate die because they want to live at least for the day-to-day. So water is an important part that we have to all look for. The electrolyzer technology, yes, of course, to produce green hydrogen or to produce alternate fuels, like doing a co-electrolysis with carbon dioxide with a solid oxide electrolyzer, we can produce syngas. And from there, you can produce a lot of other derivatives that come in. And then moving into the stationary power segment on microgrids, how can we build solutions where every house can become a power plant, every building can become a power plant, every individual becomes a contributor towards that net zero dream that we are talking about. And just recently, I mean, only yesterday, I read in the newspapers that the government has mandated that in the new capital region of New Delhi, they will not allow any energy coming out of coal from next year, from 2023. And if that is the fact, we will need to move in to new innovations on microgrids. Next comes is the mobility segment, where we are looking at hydrogen infrastructure and developing mobility solutions, especially for public transport, which will then pave way for a cleaner transportation system. Personally, I'm not a big fan of passenger cars going electric or going fuel cell. I would rather look at a train or a bus getting more stable and more greener, or an aeroplane getting greener, because that's where the world should move with. Cars are something that we should use less and less. The car industry would hate me for this, but that's my personal view. So what we do as a company, we are manufacturing electrolyzers. We make all the 4 types of electrolyzers, going in from the high capex, low capex, high opex alkaline, to the high capex, low opex solid oxide. And why do we do all of the electrolyzers is because we believe that in the future, the world will move towards the anion exchange membrane and the solid oxide electrolyzers in the next 2-3 years when they mature. But alkaline and PEM are something that are available today, which are mature today. Again, why AEM and solid oxide? One of the reasons also is that their efficiencies are good. There are also no use of rare earth or precious metals, because something that scares me moving forward, water, like I said, is something I'm really concerned on, and I'm working very vigorously on that. But platinum, iridium, cobalt, nickel, all of these materials are something that India does not produce. And therefore, one has to be mindful that when we are talking giga scale, the prices of these precious metals like platinum is not going to go down. So we as a country, when I'm talking India specific now, has to really look at technologies where we can produce everything in India, where we can even produce the materials in India. So why electrolyzers? Of course, I think I don't need to tell this. There is a big demand. Everybody's talking electrolyzers these days. It has become the darling of every person. So there is a demand, and that's why making electrolyzers makes sense. There are a lot of opportunities that are getting created even at a component manufacturing level, at an EPC level, and also electrolyzer OEM level. So even if you're talking about opportunities, employment generation, this is something which is important. These are the different market segments where the hydrogen can be used. And if this is again on an India context, Sorry, I've made my presentation very focused to India, but I think this is also one of the biggest markets, and the world is looking at India to lead this whole hydrogen race. So industry, buildings, transportation, and power, these are four basic sectors where we are going to be using the hydrogen molecule or the power to X molecule. So either if you're looking at transportation, we use sustainable aviation fuel for aviation sector, we use ammonia for the marine sector, and all of this coming from a green route. So, that it helps us decarbonize these sectors as well. The second focus area for me as a company is water. I've already mentioned that before. And there's something interesting you guys may want to read. I will not, take your time to read this whole thing. I'm going to share this presentation anyways. In 1874, this gentleman wrote that water will be the coal of the future. And almost 120, 130 years or 40 years ago next, we are seeing that happen in real. It takes 10 liters of water to make 1 kg of hydrogen. So whoever is talking hydrogen, do the math. India is talking 7 million metric tons of hydrogen. So they take your calculators out on the amount of water you're going to need. And mind you well, this water is demineralized water. It is the highest quality of water. So it goes reverse osmosis, RO water, then DM water. And within DM, then there are different purity levels that we go in. So there is a lot of energy that goes there. A lot of my friends tell me that we can always desalinate the water. There's a lot of water in the sea. And I always fear when people say this, because if we keep desalinating, maybe after 30 years, the Dead Sea in Jordan will no longer be a tourist destination, because we'll have Dead Seas all over the world. And to solve the problem of climate, we will ruin the aqua ecosystem. So we have to look at new ways to find water, new innovations to find demineralized water. Rainwater, for example, is DM water. How can we capture that, harness that, store that, so that we can use it for 12 months of a year, is something where innovators and scientists have to put their mind on. The third focus area for us is power to X, H2 infrastructure, and microgrids. So the power to X is simple. You have a carbon capture. So industries where CO2 is a problem, emission of CO2 is a problem, and heat is available, we use a solid oxide electrolyzer. With the carbon input, we produce synthetic crude, and from synthetic crude, we refine it, and we are able to produce different derivatives of hydrogen and use it in different industry sectors. Again, whatever I'm presenting here is not a figment of my imagination or something that I picked up from the internet. All of these technologies we have demonstrated. Some of these we are commercially delivering. And in India, very happy to say that I'm putting up a plant in Pune where we will produce SAF, sustainable aviation fuel, using carbon dioxide coming out of a sugar factory and electricity coming from the sugar factory, bagasse plant, of course, and using our solid oxide electrolyzers. So these are things that we are now putting on the ground and trying to build a commercial model out of this. The second is the infrastructure for electric vehicles or fuel cell electric vehicles. We're trying to build something in Assam, and that's how you see the names of the cities in Assam. We are also setting solid oxide fuel cell based infrastructure for charging electric vehicles. So those are clean energy infrastructure. If you use the coal grid to charge your EVs, you're actually doing more harm to the atmosphere than the good. So therefore, a clean infrastructure is important. And then, of course, the things connected to the nature. And this is a picture of the plant we built in Jorhat in Assam. So we are known by what we give back. And, this is what we are trying to give back to the world, is by innovating, is by doing different technology inputs that we do. One slide that is missing out of here, and I would like to speak about that also, is the work we are doing on solid state batteries. So I'll take back to this slide. When I'm talking about hydrogen infrastructure, we are working with solid state batteries which work on 50 bar pressure. And we're trying to build a 3-wheeler, we're trying to build bus using that. And that, I believe, is an area where a lot of innovation is required, is the storage and transportation of hydrogen. There is a lot of work going on the pipeline infrastructure across the world, especially in Europe. They call it the backbone infrastructure. And even in India, we as a country need to seriously think on setting up the hydrogen infrastructure. Transporting hydrogen is not the simplest thing and not the most happy thing that anybody would like to do. So transporting it through pipeline always makes sense. So the H2 infrastructure is also something which is very important to do, and where my company is working very seriously. So it's the fuel cell, it is electrolyzers, energy storage, and the transportation. And then how you integrate all of these, how you bring all these together and build a process where we can deliver a complete end-to-end solution to our customers is what we focus on. And I think that is what is also required. That's what is the call of the time today. And of course, we always believe that, and in something that our past president, APJ Abdul Kalam Saab said, that unless India stands up to the world, no one will respect us. In this world, fear has no place. Only strength respects strength. And if India is able to build itself as an energy powerhouse, we miss the boat on EVs, we miss the boat on making a Google in this country. But we do have the potential to build the largest green hydrogen or hydrogen-based derivative ecosystem, because we are generally blessed with a lot of sun, a lot of wind, a lot of hydro, a lot of people, a lot of land. So that's the best that we can do with the resource we have. So thank you very much for this.
Siddharth, thank you for excellent, very concise and detailed also, all aspects covered of hydrogen economy. Can you just explain more on swappable cylinders of this three-wheeler solid storage?
Yes, the solid state batteries that we have developed, this is again in partnership with a Canadian company. These cylinders, they work more like a blotting paper. It's like an absorbent. Therefore, we have a small 350-gram cylinder. That's the smallest cylinder we make. And in an auto rickshaw, we are putting 3 of these cylinders, which will make it 1 kilogram of hydrogen in total. And that will give the auto rickshaw the power to run 210 kilometers. And these cylinders are going to be fit with the IoT-based system where if the cylinder goes out of gas, it automatically tells you where the cylinder is available. So the ecosystem we are creating is that we have a centralized plant and we fill about 1,000 cylinders. And these cylinders will be available at every medicine shop, or in India, we call it the pan ki dukan. It will be literally available everywhere. And you can go there, remove one cylinder, put the other one. It takes less than a minute, and then you're off on the road again. So at any point in time, at least one of your cylinder is available. So if not 210 kilometers, at least 50, 60 kilometers is where you can easily go and travel. And with that concept, we are trying to build something which is a vehicle to home, a vehicle to grid, where I envisage that if I have 100,000 two-wheelers on the road, and if the grid for some reason requires power, for your sector coupling activities, or there is peak demand, all of these auto rickshaws can get a message through their IoT or through their web app, and they can go and park themselves, feed into the grid. They can start making money. In the night, they can go home, plug it into their house, and make it work. So the three-wheeler that they will have, the asset monetization will be 24/7. So the three-wheeler becomes the third earning member of the family. And that is the whole ecosystem we are trying to build around. And therefore, I always say that H2E, my company, we are not a technology company. We are a company that believes in building solutions for people, using technology, of course. We adopt technologies. But for me, the customer is the center point. The scientist is not, unfortunately, or fortunately. So whatever the customer needs is what we will give, try and make their life simpler as possible.
This is great that whatever customer needs, you try to provide him that. But what support you need from our government, our industry, our other pillars of the economy, so that this thing can be materialized faster?
I think, Rajanji, the government of the day, and very proud to say this. Not many people across the world or even in India believe this, that H2E is a result of the great work that government is doing on the whole hydrogen ecosystem. And we've been promoted a lot by the government. There's been a lot of help coming from state governments as well as the central government. And the government coming up with the national hydrogen policy is, I think, a big constructive step. No less than the Prime Minister of this country is our chief marketing man for the whole hydrogen economy. So I think you cannot get a better person to market this whole story to the world and even to people within India. And in terms of what the government can further do, I think create a realistic pathway. Of course, the vision is very grand, but we need to pick industry segments. For instance, we can pick aviation as a segment or marine as a segment and steel industry as a segment. If you say just pick 3 segments and we decide that for the next 3 years, we will make sure that 50% of India's aviation fuel comes from the SAF route, whether it is from the bio-waste route or the electrolyzer route. All your ships coming in and out of Indian ports will be...
So basically, bold decision making and that sticking to that is required.
Yes, I think
solutions will emerge.
I think more than bold, it is disruptive decision making rather than going into populist decision making.
Right.
That pick up industry and tell that industry, tell all the airline companies that we give you.
You have hit the nail. Yes. Instead of populist decision making, it should be disruptive and should be implemented. Whatever is required should be done.
And I think to a great extent this is happening. So it's very happy that whatever I'm saying is what government should be doing. The government of the day is doing in some form or the other. So which is, I think, the best part. I mean, whoever has come from the world, I want to tell you guys that there has been no better time to be alive and working in this country.
Thank you. Now I call
Siddharth, but your solution, the swappable solid battery solution ecosystem that you are generating is really a very, very brilliant concept. I should compliment you on that.
Thank you, sir. Thank you.
Now I would call Mr. Prateek Vyas from Bloom Energy, who is heading the business development and marine business of Bloom Energy.
Thank you, Mr. Rajan. Good afternoon, everyone. Thank you all for being available and giving us an opportunity. Pardon me if you hear some background noise. I'm at some public place. I would like to congratulate Siddharth and their efforts in terms of solid oxide, fuel cells, and electrolyzer. And Bloom as an organization is also happy to see a lot of organizations and players emerging in this market. What we call it as it's an analogy to solar revolution, where if we see early 2010s, a lot of companies in solar came in, and that's how solar as a technology is now viably available across the globe. And that is what we foresee happening in case of solid oxide fuel cells and electrolyzers as well. I'll talk less on the solid oxide electrolyzers and fuel cells. Siddharth covered rightly almost all the advantages of these technologies compared to PEM and alkaline. What I'll try to focus is very concisely about Bloom as an organization, what we have been doing, what Bloom's presence is in India, and what we foresee to do with our technology. So as an organization, we are a 21-year-old organization. We are listed in New York Stock Exchange. So the headquarters are in US, but we are present in India since 2005. So we have a strong presence. Out of our 1,500 employees, close to 400 employees of Bloom are in India. We have 2 offices, one is in Bangalore and one is in Mumbai. In terms of market and in terms of fuel cells market, like Bloom occupies 80% of market in United States, 90% of market in South Korea. Our installations till date are in United States, India, South Korea, and Japan. And we are now exploring a market in Middle East and Europe as well. $10 in revenue. Somewhere around $2 billion of investments have gone in research and development of this technology, what we see. The product that has come out has now seen a deployment close to 700 megawatts across the globe. When we talk about India as deployment of Bloom's technology, we have a 4 megawatt installation in Bangalore. It's in the campus of Intel in Outer Ring Road. And that's where the terminology that we say is microgrid. What we are trying to do with Intel is that we are helping them solve the problem which most of the customers face, is that the access to grid limits the expansion capability, and that is what we try to remove. We tend to help our customers not rely on grid power and come out of that and have their own captive power generation, which is available 24/7, 365. I have come up with only 3 slides, and this is the last slide in terms of my presentation, but this is the one what we intend to say various segments in which we are present. So our core platform is the same cell, solid oxide cell. When we use it for power generation, one side of a cell is anode and the other side is cathode. And when we flip it, when we put it in reverse direction, the same cell then starts working in the electrolyzer mode, right? So that helps Bloom as an organization to cater to our technology, which has already seen deployment in terms of 1 billion units already in market, to further show its strength in terms of electrolyzer market. When we talk about various segments in which we are present, fossil fuels, if you see, why fossil fuels we are still catering to this market is because the amount of cleaner power generation that is possible through it. Why cleaner power generation is because when our sort of fuel cells are deployed, one, we run at very high efficiency. So when we run at very high efficiency, obviously the fuel consumption is low for equivalent amount of power generation, and the CO2 emission is low. Second, when the systems run, there is no nitrous oxide, no sulfur oxide, no particulate matter. So you may not be getting the green power, but you're still getting clean power. In terms of India, comparing the emissions from Bloom system to what the grid emits today, we are around 70% lower. So it's like a low-hanging fruit for any customer in India to deploy this technology and abate their emissions or carbon footprints by 70% directly, to the extent they're consuming grid power. Next, you see in terms of stationary, what we can do when our systems operate in electrolyzer mode is we can consume nuclear power and the waste heat available from the nuclear power plant to generate hydrogen. Typically in the market, this is called as pink hydrogen, but the solid oxide electrolyzers are the one which could give the most efficient green or pink hydrogen generation. So I'll give you a number in terms of what amount of power that will be consumed. So somewhere around 39 units of power is consumed to generate 1 kg of hydrogen when our solid oxide electrolyzers is coupled up with waste heat available in nuclear power plant. So 2 of our electrolyzer installations, one is with IDOA National Laboratory in US, and second one which we recently announced is with Westinghouse. So Westinghouse is like 50% of nuclear power plants across the globe. The technology is provided by Westinghouse, and Bloom and Westinghouse have jointly decided to develop the market in the nuclear energy field to deploy our electrolyzers and generate pink hydrogen from there. The next one is renewable. On the good side of our fuel cells is that the same fuel cell is capable of taking in natural gas as a feed. On the same fuel cell, you can use biogas. Not just that you need or you need a purified biogas, you can use a raw biogas to generate power. And the same fuel cell, you can use hydrogen. So when a customer deploys a system over the period of time, they don't need to change any form in terms of the footprint, as they keep getting in accessibility to renewable and cleaner fuel. They can keep blending in terms of the feed to our fuel cells, and they can from the current scheme of reducing the carbon footprint of 70%, they can reduce it to 100% in future. In terms of transmission and distribution, this is where our deployment of microgrids comes into place. There are various locations and sites where grid is not available or it is too expensive to provide grid. And I also take out a leaf from the deployments or an initiative that India did is on demand side management, So there are two ways to cater to energy need is one, you cater to that energy, or second, you reduce the demand. So that's where we help in terms of reducing the load on transmission and distribution network when we deploy on microgrid. We have deployed close to 50 microgrids across the globe, panning out for data centers, IT companies, utility companies, so that all these companies are now not relying on the grid power, and the critical need to power is available and catered to 24/7. Talking about mission critical activities, majority of our deployments are with data center. If we see in US market, almost all the data centers have Bloom systems deployed, specifically catering to the mission critical power. It helps a lot in terms of relieving the data center facility, freeing up the space that is being consumed by UPS and batteries, and there are a lot of auxiliary power consumption that goes in terms of keeping the house where UPS and batteries are housed, keeping them cool. And when our systems are deployed, all those requirements are negated, not just a direct tangible saving. There's a lot of indirect tangible savings that our customers get when they deploy our system to get the critical power. Then we move in terms of transportation. I would touch upon the sea transport more, is because the marine division where Bloom has, one important aspect of solid oxide technologies is by default, since it's solid oxide, it's heavy. The weight is more compared to a PEM or an alkaline. That makes it deployable in terms of marine, but on land base or on vehicles, it is difficult to deploy them. In terms of marine, we are trying to decarbonize the entire marine segment. And what we have started is with the cruise industry. So very recently, we announced that MSC Europa would be deploying our solid oxide fuel cells to power the base load of their cruise line, which will be sailing by August of this year. We are not just catering to cruise ships, we are catering to LNG carriers, we are catering to the bunker ships as well. So over in next sea-going vessels would be deployed with fuel cells. This is also in line with IMO's requirement to reduce 30% of emissions compared to 2008 levels by 2030. So there's a huge amount of push in marine industry to achieve those targets. And by 2050, they want to reduce up to 80%. So marine environment, whether we talk about consuming ammonia as a fuel, that is also going to go, that should go up in next decade or so. In terms of land, what we are trying to do is, land, we are still working on stationary deployments only, but we are trying to cater to DC power, fuel cells being a system which does not have a rotating component. The primary form in which the power is generated is DC power. And this makes it easier to deploy to the switching networks on the switching house of railways to give them power at high efficiencies. Whereas in terms of electric vehicles, we would be working more in terms of generating green hydrogen at a much efficient rate and at a cheaper price, so that the raw feed to these electric vehicles, which would use fuel cells to operate them, the fuel is available at much cheaper and an efficient manner. So this is what Bloom is trying to do, and this is what I wanted to present. If there are any queries, please feel free to drop in.
Okay, thank you, Prateek. Now let me call Guy Downey from Levidian, Director BD and Sales. He will speak on methane pyrolysis to produce hydrogen and graphene. Welcome,
Hello,
Mr.
everybody.
Guy.
Hello, thank you very much for the nice welcome. So just to introduce myself, I'm Guy Downey. I'm Director of Strategy and Business Development for Levidian. In fact, we do not have a pyrolysis project. We use cold plasma to crack the methane. So the difference there being that pyrolysis tends to use a catalyst, which can be quite a dirty process. It's not something that we actually do. So I'm going to present some slides on what the loop technology is that will produce very pure hydrogen in the process. And I'll share that with you now if you just bear with me. Hopefully you can see that. So Lividian was actually formed about 10 years ago. We were a spin-off originally from Cambridge University in the UK, and we became a company called Cambridge Nanosystems. So Cambridge Nanosystems was a producer of graphene, carbon nanotubes, and other nanomaterials. And it was very much a scientifically driven organization. The process to produce graphene was using cold plasma. Cold plasma uses microwave technology to crack the methane in a reactor chamber. And the output of cracking that methane is a soup of ions which reassemble into usable hydrogen by volume, and also trapping the extracted carbon from the methane in the form of graphene. So what we'll show you just now is a little bit about that technology. Our company vision is a decarbonized world powered by hydrogen and built on graphene. And we're going to do that. We're going to assist many companies in their journey of decarbonization to 2030 and beyond. So what does Lividian Loop do? So Loop is actually the system that we've been using in-house to produce our nanomaterials. And we are commercializing that at industrial scale to crack methane in different scenarios. What this will do is, in decarbonization mode, it takes the methane and it cracks into a hydrogen blend and graphene. Both of those are very valuable outputs. Of course, we're here talking about hydrogen today, but graphene itself has some very, very strong benefits in the decarbonization world. Graphene is mainly used as an additive, and when it is used as an additive, it increases the performance of materials at a nanoscale. Examples of that could be where it's been used in paints, coatings, adhesives, rubber technology for tires, cementitious products, reduction of CO2, particularly with use in the construction industry of concrete, and so on. And what it does is it effectively enhances the characteristics of those materials, such as strength, compressive strength, shear strength, and so on. Graphene, of course, can also be used in battery technology and other electrical and biomedical applications at scale. In one pass of our reactor, we crack the methane and we reduce the effective CO2 emissions that would have been combusted in that methane by 40%. So at the moment, we have taken our Lividian Loop to market in the UAE. We've recently signed a contract there to deploy 500 Loop 50 scale units over the next 4 to 5 years. And we are working on similar deals around the world. We're very, very interested to assist India in the journey to net zero and beyond. The unit itself is currently containerized, and we're currently at the scale of what we call Loop 10. Loop 10 would be a 10 kilowatt hour unit. That's the energy consumption, and it would process only a demonstrator scale of 1 kilo per hour of methane. Loop 100, which I'm showing on the slide at the moment, is our industrial development module, which is really for the initial trials within a facility that's already using methane. And the methane that we use are really 3 categories. We can either use grid gas, which would be natural gas at say 98, 99% methane, biomethane as an emission in a treated methane, or biogas. And biogas, when we consider biogas, a typical biogas might be 60% methane, maybe 40% CO2 there or thereabouts. But our reactor can still treat the methane within that gas feed. It's important to say that the technology itself can cope with other hydrocarbons, and we can crack other hydrocarbons in that process. And as it says on this slide, when we actually process the gas through the loop, in the reassembling of the ions and the exhaust gas, there is the formation of heavier hydrocarbons there. So there may be some acetylene, ethylene, and ethane as 3 main components of that exhaust, as well as the balance of methane and hydrogen. So if you take 10 kilos, in this case, in the mass and energy balance shown, of the methane, you produce on one pass 2.1 kilos of hydrogen. The important the important thing to note about the energy balance on this is that the feed gas, if it's being used for a purpose such as a heat or power application elsewhere, it can still generate the same power from combustion. So for example, we've said here 150 kilowatt hour in terms of combustion value of that methane gas would be converted to approximately 150 kilowatt hours. There's very little losses in that process. It's important to note that we've stated green electricity here. So solar, wind, or other reclaimed energy source would be essential to make this really a truly green process. And in this case, at this scale, we would consume 100 kilowatt hours of electricity. Of course, we talked about graphene. In every pass of the reactor for every 10 kilos, we are extracting 3.8 kilos of graphene, and graphene in the form of what we call G3. Now, anybody that's worked with nanomaterials in the past may have dealt with graphene in different forms. Graphene is a two-dimensional lattice arrangement of carbon atoms. It's a very special material that was only discovered around 20 years ago. And within that, there are different grades and qualities. Our process produces graphene from the atomic level up. So we refer to it as pristine graphene. And in fact, the graphene that is produced is fuel layer graphene also. So we actually produce in our facility in Cambridge two forms, G1 and G3. G1 is between 1 and 3 layers of that material, and G3 is typically between 8 and 10 layers of that material. It's very pristine. Because we don't use any catalysts and there's no other contaminants in our feedstock, we produce a very, very fine and high quality grade of graphene that's consistent because the process works on steady state. Two configurations for our loop system. So we can configure simply to decarbonize an existing gas stream, and usually that will be the decarbonization of the gas by 40%. It obviously produces a hydrogen-rich exhaust output, and that's roughly 75% by volume. The graphene is then harvested from the process, and we, as Levidian, will take that to resell to our graphene customers where that's used as an additive. We can also deploy the loop to companies or organizations that may have a use for both. I'll mention here that we're currently doing a project in the UK with National Grid. So this is the network of pipelines for the National Grid gas in the UK. They are exploring integrating our loop technology into their infrastructure to produce hydrogen and to increase the hydrogen content within the grid gas. But in order to do that, they have to consider the reliability of the network and also the possibility of damage to the network with the use of hydrogen through hydrogen embrittlement. So an interesting area that we're working on them with is for coatings of pipework, where graphene is actually being used inside the pipe coating itself. And because of the very fine nature of the material, it gives a hydrogen barrier. So it prevents the hydrogen reaching the substrate and causing that hydrogen embrittlement.
You have 1 minute more.
So hydrogen separation is the next part. So we have a hydrogen separation capability. This is the second configuration. This is where we produce 99.999% hydrogen for use in fuel cells and so on. Importantly for this and for this context, this technology can be produced at scale to suit the customer. So it could be for a filling station, for example, where you have a local grid gas and you can convert that. It can be a waste gas site where there's actually landfill and so on, or anaerobic digestion facilities and so on that can actually be deploying this technology and producing localized hydrogen sources. So you can very quickly build up a hydrogen network using our technology. And that's basically the overview of the technology within the time. So I'll hand over to the organizers. Thank you.
Thank you very much for the very nice presentation. Now, is Mr. Chandrasekhar from KPIT with us? Yeah. Chandrasekhar ji, please, you are invited to speak on your biomass to H2 and other technologies which you have developed, and some of them have been transferred. You have 5 minutes to 6 minutes. If there is a problem in sharing the slides, you can speak out simply. We can understand.
Yeah, can you hear me?
Yes, yes, perfect.
Yeah, sorry, there was some problem with the unmuting. So, thank you, Rajan, for inviting us here. So myself, Chandrasekhar Chincholkar from KPIT Technologies, looking after electric mobility and clean technologies, strategic advisory. So, as a company, we are 100% focused on automotive technologies. We are a pretty large company with $350 million of turnover and a profit of around 275 crores last year. Around 6,800 technologies, 25 even innovation awards, 51 global patents, and we spend large amount of our money on R&D. So, our focus areas are basically, electric powertrain, autonomous driving, connected vehicle diagnostics, mechatronics, and AutoSAR. So we have presence in around 20 locations worldwide. 4 locations in America, then 7-8 locations in Europe, and rest in Asia. So, as most of you are aware, the entire world is actually moving towards hydrogen. So these are basically the countries which are part of the hydrogen mission. Even India has actually now, with the announcement of hydrogen energy mission, India has also become part of the energy in the hydrogen world. If you look at the world, actually how they are moving in terms of hydrogen economy, the number of countries, the number of companies, and the number of funds actually which are moving closely towards having the changing preferences towards green economy and hydrogen economy. So these are the companies which are actually contributing or believing in this entire trend. And the current assets under management is roughly around $31 trillion, and these number of assets are actually going to increase in the significant number in the coming days. If you look at our first ground-up innovation, we have developed the first PEM fuel cell in the country. Very effective solution. The efficiency is around 50%. It is almost double that of a diesel engine. It can actually be, our cost currently is in the range of $1,000 to $1,200 per kilowatt. With higher volumes, the cost will actually drop significantly in the coming days. We have actually, demonstrated the first hydrogen fuel cell bus also, which I show the photographs also. Other than this fuel cell, we have developed the powertrain technology, which is so critical for a battery electric bus as well as a fuel cell electric bus, because both fuel cell as well as the powertrain together actually make the vehicle more efficient in the domestic vehicle scenario. So if you look at the battery electric vehicle, it is the motor controller, transmission, BMS, vehicular ECU is something which is our own patented technology. The designs are with us actually. The fuel cell is also complete 100% ground up we have developed, and our energy efficiencies today is one of the best in the country. It is around 0.65 kilowatt hour per kilometers, and it is definitely contributing towards Make in India initiative for the government of India. If you look at this particular car, this was a project done by us along with CSIR Pune, and this was the first program done under NMITLI research program of Government of India, and we demonstrated the first Mahindra Verito vehicle retrofitted with a fuel cell, and this particular vehicle was demonstrated in the month of October 2020 within the CSIR premises in India. Post this, we actually started working on the bus, first fuel cell bus in the country, and we actually done the retrofitment of the first fuel cell bus. I show the photographs of the bus. So this is the bus which was actually launched on 15th of December 2021. In the middle is our chairman, Mr. Ravi Pandit. On his left is Dr. Mashelkar. On his right is Dr. Ashish Lele from NCL Pune. So, other than this, our contribution is basically towards developing these two technologies. One is the anaerobic digestion route, where we have actually tied up with Agarwal Research Institute. And if you look at, the current technology, it has actually got 25% more yield as compared to, the normal route. It can actually use, raw materials such as rice straw, wheat straw, napier grass, and the other, other products, byproducts, which actually be produce our fertilizer, organic manure, and CO2. So this is a very environmental friendly technology. This has been demonstrated at the lab scale, and being the first, globally first technology, we actually filed a patent for this. The second technology is basically hydrogen generation from gasification of biomass. Here again, the yields are very good. If you look at 25 kg of biomass can actually produce 1 kg of hydrogen. So the yield is in the range of, almost 4%. Currently, our plant is in operation in Baroda. And here in this process, particularly from the woody biomass, we first produce the syngas. And from syngas, we actually produce the hydrogen. So our current pilot plant of 125 kg per day is actually operational. And the raw material that can be used for this is basically, soya stalk, cotton, bamboo, forest wood, bagasse, etc., including MSW also. So the byproduct for this particular process is basically biochar and CO2. So this is again a very efficient process, and we are trying to scale up the plant to a larger plant in the next few days. But obviously, this is something which is working very well in Baroda. So I mean, just a fact to state is that how hydrogen economy can actually contribute and meet the sustainable development goals of the United Nations. So out of the 17 goals, we can see almost 7-8 goals are actually something which can be met through hydrogen economy. So these are areas, because everybody today is talking about environmental, social, and governance, and what we actually cover under ESG parameters is most of the 17 sustainable development goals of the United Nations. So from a startup ecosystem point of view, as discussed with you, Rajan, what should be the focus of the companies which are there in the startup field? Technology usage and application is very, very important. Commercialization is the biggest important effect of any R&D that needs to be done. And obviously, the fact is that you need to have a continuous cost reduction process in mind, so that you can actually lead to look at more penetration in the coming days. Initial funding is obviously important. Create a POC. Proto demonstration is also very, very important. The bigger challenges actually come in terms of addressing the scaling up issues, and these are the areas which needs to be focused by an entrepreneur. Getting either a strategic partner or financial partner is also very important, because without that, the growth will actually not come in. One very important parameter, like business, we call it as a very dynamic situation. On a day-to-day basis, we keep changing our strategy and attitude. So in R&D ecosystem also, I would suggest one should look at a dynamic sort of a situation, so that people are able to adapt to changes very quickly and are able to come out with a solution which can actually be a winner in the long run. So obviously, all of us are now trying to address sustainability and climate change in a big way. So this particular idea or this particular concept obviously has to be part of every solution that we actually come out in the coming days. So, this is a brief of our work that we have been doing, and any questions are there, I can take it up, or maybe we can share my mobile number or email ID, and I'll be happy to.
Okay, yes. Thank you, Chandrasekharji. I'll share the questions which we have later on with you separately. And now I call Mr. Mahesh Pagnis from CEO. He is CEO Paramhans, and he has developed methane splitting indigenously here in India. Rudra, he has patented as a Rudra reactor.
Good afternoon, everybody. I'm Mahesh Pagnis from Magnesium Innovations Private Limited. Our company name stands for people. That's Magnesium. We are in producing the light. having pyrolysis. We have.
Are you connected with the mobile or through what Wi-Fi? It seems both the things are on.
Now, is it audible now? Hello?
Yes, it is.
Okay,
It is
fine.
audible.
Yeah. I am Mahesh Pagnis from Magnesium Innovations Private Limited. Magnesium Innovations Private Limited, if initials you take, that defines our goal. PIPL for people, we stand for people and we try to fuel the life. We are in pyrolysis business for last 12 years and we have delivered lot many plants in Europe, South Africa, Turkey and US and UK as well for pyrolyzing the agro waste for many value-added products like biochar, wood vinegar for organic pesticide and lot many things like that, and fuel as well from waste tires, plastics and this and that for last 12 years. Recently we came across this need of hydrogen. Actually, when I started studying hydrogen, I came to know that India's consumption of hydrogen per hour is around 1200 metric tons per hour. This is Terry's report in 2020. So if we produce hydrogen by SMR, as on today 98% of hydrogen is getting produced by SMR, that means we are producing 4.5 kg of carbon dioxide, not less than that, per kg of hydrogen. This means we are emitting 4,500 metric tons of carbon dioxide every hour in our environment, and that is why it was painful for me to digest it. So I started working on hydrogen. There are a lot many methods for hydrogen, and my very much good friends were here and they explained lot many methods like getting graphene and getting from electrolysis, but I really don't know how to connect our farmers to the energy sector, and there I'm heading right now because I wanted to build a very small unit suitable for our biogas plant owners. These farmers are in rural area, and the hydrogen transportation is also very costly, so it should be a decentralized manufacturing of hydrogen. That was my goal, and we are here. Actually, when I came to know that this is what we need to do, then we started working on the pyrolysis of methane to split the methane into hydrogen and carbon, and finally we did it with our very small unit, 2 kg per hour unit, where the 8 kg of methane can get split into carbon 6 kg and 2 kg of hydrogen. So what happens next is I'm sorry, I couldn't share it. Okay, all right, I'll speak.
No problem.
Yeah.
You have another 2 minutes.
So before 2 days, I posted one post on the LinkedIn, and I'm very much thankful and grateful to Mr. Rajan to invite me here among the all genius people all around the globe, and a lot many people they thrown a light on say usefulness of hydrogen, that we already agree on that hydrogen is very useful. Whereas my one question to all of you is, how far it is better to transport the electricity than that of hydrogen? If we put the fuel cell and create energy or power, and we convert that, we transport that electricity to the desired destination, it will be better. Or we have to put very small units for every farmer who is producing biogas, and from biogas to methane, and methane to again hydrogen, that will be more beneficial, so that we can transport the small amount of hydrogen to the existing our roads, where the hydrogen dispensing units will be set up, and there, like our farmers deliver the milk, he should deliver the hydrogen. See, unless it is the activity is supported by money, and if our every single person in the supply chain, or unless our the last poorest person is benefited by the technology cannot be accepted. And this technology, at least when we are thinking of going for say global or environmental and global warming and this and that, we have to stop our farmers burning the wood in their farms first. So, and for that we have to pay him. If we want to pay him, we have to take something from him, and there we can take the hydrogen. That is why my unit is hardly 2 kg hydrogen production unit. It is very simple. It consumes hardly 20 kilowatts of energy for 2 kg of hydrogen production per hour. And with a small village with say collectively 10-12 farmers, it can be done. My ask to government is, fund the farmers. They will purchase my unit and I will be benefited. Don't fund me. I don't need your funds, but my farmers, they need funds. I'm talking from my bottom of my heart, because till 10th standard, I was in farms. I worked in farms by the weekends, get some money for my sleepers, and then went to the school by walking for at least 6 kilometers a day to and fro. So I know the pain, and I know where the money should go. You know what? From the solar, first rupee comes to our market, that comes from the solar to farms and farms to market. It never goes from market to farmers. Now it's our turn to give that 1 rupee back to the farmer. If 80% our India are the farmers, then this is the right place. This is the right market for the hydrogen for use and production. We should go there. We shouldn't think of big people. They are already have done enough for us. They are doing, they are creating jobs and this and that. Okay, that's okay, fine. We have to decentralize, we have to democratic production of hydrogen. We need that one. We need a decentralized, so that we should save on the transportation of hydrogen. If we produce the hydrogen by green way or blue way or bluest way, and then again we transport that hydrogen by burning diesel or petrol, what makes the sense? I don't think so. So this is my offer to everybody, that I have built one machine. It is in the it is on the stage of POC. I agree, but POC is right enough for me to generate some funds. Some financer will be there, and within say 4 or 5 months, I will be going commercial, and my whole unit, along with the PSN, everything will fit into a container. It is a modular type. You can fix 10, 15, 20, whatever numbers of modules you want, and accessories you can put in common, produce whatever hydrogen you want to produce. And if at all we go for in say drought areas where the water is not there, and produce some biomethanation and then hydrogen, then fuel cell will produce even a good quality and quantity of water as well. So this will be the circular economy, I think, because farmers, they need now organic fertilizer that can come from the fermentations and biomethanation plants, and then methane can be used for my Rudra, There we can buy back your carbon black. It goes directly to the tire industry, paint industry, plastic industry. And you know what? How much carbon black we need? We, as a India, I have heard that we are importing 4 lakhs of tons carbon black every year. Now, BKT is producing, Continental is producing, Philips is producing. How they are producing? They are burning the fossil fuel and they are producing the carbon black. See, there are so many, unknown areas, dark areas where we are generating our carbon dioxide. So we have to stop those things. We have to go by, to grassroots level for this particular thing, which we did in past few attempts, that we did so many things on a peripheral way and we failed miserably. We means not we.
Thank you, Mr. Mahesh. Thank you for heart-to-heart discussion and providing the country a solution which can be easily replicated. And all the best for the commercialization of your module.
Thank you, sir.
Thank you. Now, can I invite Miss Emmy Kessler from Pensaco Technologies, USA? Miss Emmy, are you connected? Yeah, please. Miss Emmy, please unmute yourself. देखना उनको unmute कर.
I am on.
Yes, you are audible.
Unmute. Can you hear me now?
Yes.
Okay, great. So I'm Amy McRae Kessler. I am Chief Commercialization Officer for Pensaco Technologies. And I just wanted to thank you for allowing me to present today and be in such incredible company with all of these very brilliant people who are working hard to address our climate crisis and position India as a leader in doing that. So Pensaco produces carbon negative green hydrogen and permanent carbon removal at the same time that we produce our hydrogen. And we do this by recycling biomass waste and other wastes to produce carbon negative hydrogen, as I mentioned, green hydrogen. We permanently remove carbon dioxide from the atmosphere. And in our platform of products, we are solving multiple global challenges that address markets that are worth trillions of dollars. So as you're aware, the climate crisis has gotten to a point where carbon neutral energy isn't enough, and just reducing emissions is not enough. The IPCC, IRENA, global corporations and governments around the world have recognized that we need to start permanently removing carbon dioxide from the atmosphere in very significant amounts, 10 billion metric tons a year between now and 2050, and then 20 billion metric tons a year after 2050 to meet probably our 2-degree goals. And in order to do this, carbon negative bioenergy with carbon capture and storage needs to grow about 14% a year. So Pensaco has come up with a model where I'm wondering if you can, this is too big to be seen, but our model is to take waste, CO2 and biomass and process it into renewable electricity that can be fed to an electrolyzer. We produce hydrogen through a thermal conversion pathway, and then carbon products, which sequester biogenic CO2. And that allows us to address sustainable waste management, carbon negative energy, biochar, which has many uses that I'll get into. And then we're addressing the climate situation by permanently removing CO2 as well as reducing emissions. So we're kind of at the very leading edge of this carbon negative transition. Our green hydrogen, we produce it outside normal syngas production pathways. And that allows us to produce a very clean, high purity stream of hydrogen from biomass waste. We get between 85 to 110 kilograms of hydrogen per ton of biomass, which is about 3 times our thermal conversion competitors. And it is 4 times the yield of hydrogen per megawatt of wind or solar at about 8 times less the cost. So it's a significant advantage over wind or solar technologies for producing hydrogen. And we're currently at about $1.50 per kilogram in terms of production costs, and should be well under $1 by 2030. Other advantages include that we produce hydrogen 24/7, baseload supply, which makes us ideally suited for mobility applications, microgrids, which we very much believe are the future of energy to get decentralized sources. We are able to decarbonize agriculture through either the production of green ammonia and our biochar. And also those we're able to help with industrial decarbonization, again, through biochar and our green hydrogen. So carbon removal has become a big priority for the world, and our biochar is one of only 5 pathways that exist in order to remove CO2 from the atmosphere permanently. And 1 metric ton of biochar removes about 3 metric tons of CO2. It's a permanent, durable removal and sequestration. Lasts about 1,000 years, and it generates the most lucrative carbon credits in the marketplace. They're currently trading from anywhere from about $120 up to $600 a metric ton. So for each of CO2 removed, so for each ton of biochar, you're generating 3 of those credits. So it's a very significant stream of revenue that I think will help adoption of the technology and use of biochar in rural areas. And as I mentioned, it has a number of environmental benefits, helping with replenishing soils to increase crop productivity, conserving water, and reclaiming marginal lands for productive use. So our technology is an advanced integrated pyrolysis and gasification reactor system. It integrates the best of pyrolysis and gasification into one reactor. And through a proprietary use of process air, we're able to generate a material and energy balance that is greater than 100%. So that allows us to produce 30% more energy from our feedstocks. And it allows us to generate all the energy we need to run the system. We need no external energy at all. And we also are able to set up different zones within the reactor for pyrolysis, energy recovery, and gasification, and really have a precision control system that allows us to produce bespoke products. Like if you want to have a special carbon product, we can make that. If you're looking for specific biochemicals, hydrogen to a certain spec, or green ammonia, we can do that as well. I'm going to go kind of fast since I know we're running out of time. One of the things that we've done is to innovate a dual stream pathway. And that is where we use our reactor system to generate electricity. And that electricity powers the system, and then excess is sent to an electrolyzer to produce green hydrogen. And then we also have
thank you. You have 30 seconds more.
30 seconds. Oh,
yeah.
okay. Well, it's that's too bad. We're available in multiple configurations. Will I be able to share the presentation afterwards with folks so they can learn more about our technology?
Yeah. You can share me. I'll share that. Yeah.
Okay, great. Anyway, the point is that we do more than just green hydrogen. We're also removing carbon dioxide from the atmosphere, and that is an industry that's going to be a $15 trillion industry. We're able to use marginal low value feedstocks, so it's perfect for going into rural areas. We have a partnership established with Huta Industries, who is working in Nagaland, and we're looking to expand to make green ammonia while we wait for the hydrogen infrastructure to be developed in India. And we think that greening up the ammonia production, which is going to grow significantly in India over between now and 2050, is a wonderful way to decarbonize and help with agricultural production. I apologize that I didn't get to go through a lot of this. Let's see if there's...
Okay, thank you. Now let me call Mr. Parimal Saha, who is in research and development since last 20 years, and he has been researching in and producing POCs for various applications of hydrogen. Mr. Parimal, welcome. पाँच बजे एक बंदे को टाइम दिया होगा ना लास्ट को एक्चुअली इसमें मतलब हो गया है क्या करें ऐसा करना नहीं ऐसा करना ब्रेक अब लोग पी लेना मैं उसको तो पता नहीं चलेगा मैं बैठा हुआ उसको बोलने दूंगा वो ठीक रहेगा
Hello, am I audible to all of you?
Yes.
Okay, so thank you for inviting me to start with. Hello? Hello?
हाँ आपकी आवाज आ रही है अपना स्पीच दे दीजिए 5 मिनट 7 मिनट मैक्सिमम
3 minutes, 7 minutes, be precise.
Yeah, it is 5 to 7 minutes in between.
You cut
6
off
minutes.
Amy with 30 seconds warning. That's like, don't be so brutal to me.
No, it is not that. Actually, we have to close the session by 5:10. Our organizers have asked us. Yeah.
4 minutes, I don't mind that, but be clear about that. Yeah, okay, so is my screen sharing working? Do you all see my slide?
No, we are not seeing your slide.
Okay, sir. Yeah, so you know what? We wasted nearly 1 or 2 minutes in this. Okay, so I guess you can see it now.
Yes, it is there.
Okay. So hydrogen is basically into hydrogen fueled or hydrogen powered regional vertical takeoff and landing vehicles. And because we wanted to be into the hydrogen, so we got into the whole hydrogen value chain. So right from hydrogen production technologies to hydrogen storages, to the dispensers, to the fuel cells and the vehicles or applications that would use hydrogen for mobility. In the mobility, we are targeting air ambulance, disaster management, rescue, stuff like that. I'm going a little fast, sorry. If at all you want me to go slower, you can tell me. Basically, India is facing a big, huge problem of transferring patients from rural areas to the hospitals or to the doctors. I've seen it personally. So this has been my mission since some years now, and finally I have got the right technology to address this. Hydrogen will start with cargo. This is going to be cheaper than road transport. I'll explain further how it will be cheaper than road transport. I'm going to skip some slides. On the hydrogen side, like Gazi was using we are also using something called cold plasma. But we have a very, very unique reactor design, wherein there is a very natural kind of cooling there. And that's why we are going to be manufacturing or using hydrogen at nearly below 50 cents, right? Typically, electrolyzers use around 45 to 40 kilowatts of electricity. Our target is to make hydrogen with just 2 kilowatts of electricity. These reactors are going to be very small, so we can place it right at the dispenser. So you don't have to get into the trouble of transporting hydrogen. That's the uniqueness of our reactors and our hydrogen production technology. So we have done some basic work on the plasma. As you can see, so we had plasma reactions, and we were very happy with what reactions we had. After that, we come to our fuel cells. On the fuel cells, we are already on bipolar plates. We are working on the bipolar plate, anti-corrosive and highly conductive coatings. We are working with like titanium aluminum carbides or titanium silicon carbides, matte phase syrup coatings, and we are also working titanium plated bipolar plates. These are all techniques we are using to make the bipolar plates cheaper. Our goal is to make very, very cheap fuel cells, but these are high temperature fuel cells. High temperature fuel cells are very, very advantageous. We have already successfully developed the high temperature fuel cell membrane. The proton exchange membrane is already developed. We are using a PBI membrane. So this will be a most economical membrane for fuel cells. For the motors for the VTOL, we are making something called a hubless rim-driven motor. We call it a ring motor, or you can say a rim-driven motor. And we are going to use 3D printed copper as the coils, and carbon nanotube fibers, and carbon nanotube doped copper. This is going to be a very, very revolutionary motor and the propeller design for the VTOL. That's about it.
Thank you, Mr. Parimal. Now
Pleasure.
I call Mr. Rajesh Ayapsaru from GPS Renewables to discuss about SMR. And please be brief because we have time constraint. Thank you.
Yeah, not a problem. Yeah, am I audible?
Yes.
Okay. So I'll just get into brief of what we do. We come from a different aspect of what the entire number of people here are at. So we come from the biogas side of the story. We have, it was our genesis was through the Government of India, Department of Biotechnology. That's how we started our journey. As we grew forward, we had we have now grown significantly from 2012 to 10 years now, looking at decentralized biogas plants, which is one of the most successful captive biogas solutions, with many global firsts. So this shows the kind of customer base and the kind of partners that we're working with for the biogas space. This is how we have grown. We have won multiple awards starting from 2012 onwards, including the WWF Climate Solver Award. And last year, we were one of the highly recommended, 2020, we were recommended as one of the best plants by World Biogas Association and ADBA of UK. We have built multiple things. So we have gradually, our growth story is slow. So this is our just view of a biogas plant. We have containerized solutions for exports as well as for minor plants for smaller plants for India, and in a few places on-site fabrication also. What you see on the right bottom side is one at Intel, where Prateek was talking about his Bloom. Our plant sits right next to the Bloom Energy plant at Intel in Bangalore, the first biogas plant that Intel had done. We have an online monitoring system, etc., etc. This is one of our core areas for our system. So and we have now scaled to a level where in February, we commissioned what is Asia, Government of India called Asia's largest source segregated organics-based bio-CNG plant, and started dispensing. And as of 2 weeks back, we have touched the capacity of 500 tons of processing of source segregated organics per day, and dispensing bio-CNG for transportation in the city of Indore. So what we have, based on our experience in biogas, we wanted to look at other areas where renewables can play a role. And that's where we are clear that we are not good at everything. So we have to look at people whom we can work with our core in biogas and bio-CNG, and the way we have developed. In fact, if you see the timeline, this entire system was set up in less than 1 year, which is, you don't know whether it's a record or not, but we believe it is. So we wanted to see whether, from the biogas or the bio-CNG space, how we had discussions with multiple people, and then we have tied up with a company called Hygear initially. Now it's called ACBHPE, for their decentralized versions of hydrogen units. And here we specifically wanted to talk about the SMR variety that they have. So we have an association where the core comes from ACBHPE and the rest of it, including everything related to installation, commissioning, the gas storage, compression, bottling, the rest of it, the project management can be handled by GPS. This is the model that we are working on. The base system that is promoted is called High Stream, a containerized version. Of course, let me tell you, we are learners and explorers in the space. We are not masters of this domain, but we intend to, learn from them. So we have the solution starts at small capacities of 50 nm³ per hour and goes up to 150 with a purity of 2.5 grade up to 6.0 grade. Okay, this I don't think you should know. So essentially, by decentralizing it, we feel, because from the biogas space also, we had focused on decentralized biogas production, which enables even small scale customers to get the best out of the biogas units and the waste from their internal sources. We also feel that there is alignment where we can look at decentralized solutions for hydrogen, which includes the cost savings and also reduction in emission due to non-transportation. A lot of things are, we don't have too many manpower for operating these plants. These are remote operated. No dependency for a third party to, in terms of generating your own green hydrogen. This is just a brief that we have.
Thank you, Rajesh ji, for sharing the required details. Now, as a part of strong ecosystem, we should have trained manpower also. And Dr. Devesh Patra, ex-ED from BPCL, has been promoting an institute called Indian Energy Skill Development Institute for providing trained manpower to the country. Now I welcome Dr. Devesh Patra.
Thank you, Rajan. It's great to be here amidst these hydrogen warriors. I am Dr. DC Patra. I am speaking on behalf of Indian Energy Skill Development Hydrogen Program. And it's a associate company of Sunmarg Infrastructure, and whose director is Mr. Sanjay Kaul. He is a highly acclaimed academic innovator and institution builder. He has been instrumental in founding University of Petroleum and Energy Studies, Dehradun. The mission and vision of this hydrogen program of IESD is to impart training. And if we look at the hydrogen landscape in India, we have a lot of favorable factors. There are the regulatory environment for generation and transmission of renewable energy that does exist, and hydrogen policy is being formulated in modular form. Investment ecosystem is getting built up, R&D is promoted, multinational collaboration is taking place. Now, if this promise is to be translated into reality, then what is required? Now, this IESD hydrogen program is specifically springing from this. Now, what is required is awareness, skilled manpower, whereabouts, the orientation, and research and pilot. Now, IESD is cultivating innovation, knowledge, and certification. Now, we know upskilling is very much required in the industry to understand the ecosystem, the value chain, the economics, and to carry forward the energy transition that is taking place leading up to net zero, and meeting the skill gap for hydrogen and hydrogen-derived projects. And the flagship program of this IESD hydrogen program is an ongoing certification program. It's a 90-day certification program. The program is known by hydrogen technology application and its economics, and it is designed for primarily working professionals, entrepreneurs, consultants, and students. It is web-based learning management system, self-paced, ongoing, and the time management is flexible in the hands of the students. And it's, of course, comes with a very, very reasonable fee. And it is one of the kind program in India.
Thank you, sir, for sharing the details of institute and the hydrogen orientation of the program. Now I'll invite Dr. Sarit Das and Dr. Ambika from IIT Hyderabad. They will speak on hydrogen park on wetlands. Please be brief and let us understand what you are doing.
Yeah, good afternoon, everyone. Thank you for inviting us. We are just starting into the hydrogen field. Let me share the PPT. Yeah, so we have been working on clean energy. It's not just about hydrogen, but also we need to stop the generation of methane. So we have been working on the organic field where we got methane in the paddy field, as well as landfill and wetlands. So this project is about assessing the generation of methane, intervening the process, and convert as much as the H molecules in hydrogen. So we are cleaning the environment as well as we are generating clean energy. So that is our dual objects for this study, and we are in the feasibility study. We'll start with the lab scale and then we'll move on to the field scale that has a business potential. So myself is Dr. Sarit Das. I was ex-faculty of IIT Roorkee, and now I formed a private limited company for doing this innovation work. We are getting some funding from the DBT recently on the organics, and we are moving on to the collaboration with IIT Hyderabad with Dr. Ambika for catalysis application in this field. So hydrogen, as you already know, that is a clean, sustainable thing, and definitely the methane is treated as a carbon bomb. So how to separate the carbon particles from hydrogen before it is forming? So that is a big challenge. And if we can do that with this project, not just a wetland, but everywhere the natural process we convert into the clean thing. So everything will be clean and no carbon is going into the atmosphere. That is a big advantage for this project. We are going to the very basic science of this, and we'll deal with all the chemical and biochemical processes that is for very much common to these wetlands as well as the landfills. I worked on the landfill in US for a couple of years, and then the catalysis, Dr. Ambika is a specialist, so she will just continue with from this onwards, then I'll come back. Dr. Ambika.
Yep, so I'm here. So can you change the slide?
Yes, we are hearing you.
I could see only the title page.
Is it visible?
It's visible,
No,
but it's in the title page.
Your opening slide is visible, but you have 1 minute only now.
Okay, so I can quickly tell without
Just
the slides
speak it,
also I can
Yeah.
talk. Okay, so I have nearly 10 years experience in handling the nanoparticles. So I have all expertise to synthesize, characterize, and apply the nanoparticles for environmental and energy related applications. And so in IIT Hyderabad, we have all the facilities to synthesize the nanoparticle in the laboratory scale and try to apply it for any kind of lab scale and pilot scale experiments. So we have all such facilities, and I have all the expertise. And recently we have started collaborating with Dr. Sarit Das, and I'm looking forward for a positive collaboration and more output. Yes, this is from my side.
Thank you, Dr. Sarit and Dr. Ambika.
Yeah,
and we thank all the participants who have just a second. Just a second. Yeah.
Yeah, it's the last slide.
Just wanted
we are trying to collect the
one
hydrogen.
thing. Yeah. Right. That's fine. Thank you. And we thank all the participants through Zoom link who have enlightened us about their work and their planning and what they need from ecosystem and how the hydrogen ecosystem can be developed and enhanced further. Thank you all.
Thank you.
Sir? Hello? 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 Hello?
Participants have gone for tea break actually, so I will not be able to handle your query right now. But you can give me one-to-one, I will share that.
Yeah, okay. So we need contact details of all the presentators. So, we can get in touch with them.
Okay, sure.
Thank you.
Okay, bye-bye.